Imagine needing to truly grasp a complex scientific chapter, not just skim it, but without that, daunting, dense textbook feel. That's precisely our mission today. Welcome to the deep dive, where we're plunging headfirst into Chapter 4 of Advanced Organic Chemistry, Part B Reactions and Synthesis. Fifth, the title of our adventure today, Electrophilic Additions to Carbon Multiple Bonds. Our goal for this deep dive is really to extract the most important nuggets of knowledge and insight from this incredibly rich source material. We'll meticulously unpack the what, the how, and the why behind these critical reactions. We're exploring how new connections are strategically formed, why certain atoms prefer specific attachment points, and what the profound practical synthetic implications are for building intricate molecules. Think of this as your personalized shortcut to being well-informed, packed with surprising facts and maybe just enough humor to keep you hooked on this elegant dance of electrons and atoms. By the end of this deep dive, you'll not only possess a clear, robust understanding of how chemists precisely construct complex molecular architectures by adding new pieces to double and triple bonds, but you'll also gain, I think, a profound appreciation for the ingenious strategies that underpin modern organic synthesis. Okay, let's unpack this. So, to kick us off, let's establish the fundamental players in these reactions, the electrophile and the nucleophile. These two terms are, well, they're central to understanding everything we're going to discuss today.
That's absolutely right. At its core, an electrophile is literally an electron-loving species. Think of it as being electron deficient, right?
Yeah.
Often carrying a positive charge or maybe just a partial positive charge. It's constantly on the hunt for electrons, like a hungry magnet for negative charge.
Okay, makes sense.
And then on the flip side, a nucleophile is nucleus-loving, which means it's electron-rich. It has a surplus of electrons, perhaps a negative charge or a lone pair, and it's actively looking for a positive center to, share those electrons with. This fundamental push and pull, this attraction, drives a vast array of organic reactions.
So the fundamental mechanism for these additions generally involves what we call polar intermediates or transition states. The electrophile, naturally drawn to the electron-rich pi bond of the alkene or alkene, that's the double or triple bond, it kicks things off by attacking. This initial attack generates a temporary positive charge, what we call a carbocation intermediate, or at least a highly polarized transition state where charge is building up. And then, almost immediately, a nucleophile, with its abundance of electrons, rushes in to capture that positive charge, completing the addition. It's like a rapid two-step dance.
Exactly, a very quick dance. And the primary synthetic power of these reactions is incredibly significant. They allow us to introduce new functionality at those carbon-carbon multiple bonds. This means we can precisely add new atoms or groups of atoms, fundamentally changing the molecule's chemical properties, and importantly, opening up pathways to much more complex and useful structures. It's really how we build molecular complexity from simpler starting materials.
Now, here's where it gets really clever, I think. Sometimes the nucleophile isn't just floating around in the solution. It's actually part of the same molecule as the double or triple bond.
Intramolecular reactions.
Yes.
Exactly. This is what we call an intramolecular reaction, and it leads to the formation of new rings, a process known as cyclization. And this isn't just some chemical curiosity. It's a very powerful synthetic method, especially for creating heterocyclic rings. Those are rings containing atoms other than carbon, like oxygen or nitrogen, which are super common in drugs and natural products.
And we see two main ways this can happen: exocyclization and endocyclization. Think of it like this. In exocyclization, the new bond forms outside the ring that's closing, maybe creating a side chain off the new ring. Whereas in endocyclization, the new bond forms inside, becoming part of the actual new ring structure itself. It's all about how that new ring forms relative to the bond that's effectively breaking or being attacked.
Right. The geometry of the attack matters.
Exactly. And it's crucial for us to keep our focus clear today. This type of electrophilic addition, driven by these polar intermediates, is distinct from other kinds of additions, things like nucleophilic additions to electrophilic alkenes, or concerted cycle additions, or free radical additions. Those are fascinating in their own right, but they operate differently.
Right. Different mechanisms entirely.
Precisely. Those are topics perhaps for another deep dive. Our mission today is to thoroughly explore these electrophilic additions and the polar intermediates they generate.
All right, let's zoom in on a truly classic example that helps illustrate a foundational principle in organic chemistry: the addition of hydrogen halides, things like HCl, HBr, or HI, adding across alkenes. The observation that really revolutionized our understanding here was made quite early on. When you add hydrogen chloride or hydrogen bromide to an alkene, the halogen atom, the Cl or Br, almost always attaches to the more substituted carbon of the original double bond. So the carbon that's already got more other carbons or alkyl groups attached to it.
This consistent directional preference is so fundamental and predictable that it earned its own name, Markovnikov's rule. And when we say a reaction is regioselective, we mean it shows a strong preference for forming one particular constitutional isomer over others, especially when you're working with unsymmetrical alkenes, where, there are multiple possibilities for where things can attach. It's essentially about controlling where the reaction happens on the molecule.
And the mechanistic basis for Markovnikov's rule is fundamentally about carbocation stability. Isn't that right? The initial step involves a proton, H plus K, from the hydrogen halide, either fully transferring or maybe just partially transferring to one of the carbons in the double bond.
Right, initiating the attack.
And this creates a carbocation intermediate, a carbon atom with a positive charge. The key here is that the relative stability of the two possible carbocations formed from an unsymmetrical alkene dictates which pathway is favored and, therefore, which product dominates.
Exactly. And more substituted carbocations, like tertiary ones, than secondary, than primary, are significantly more stable. Why? Well, think of it like this. Nearby alkyl groups, or even aryl groups, like phenyl rings, can subtly donate electron density. They do this through phenomena like hyperconjugation and inductive effects, which help spread out and stabilize that fleeting positive charge. So you'll see a stability trend. Primary carbocations are less stable than secondary, which are less stable than tertiary. Benzylic carbocations, next to a phenyl ring, are often even more stable.
Okay.
Once that more stable carbocation forms, the electron-rich halide anion like Br or Cl rapidly attacks it, completing the addition. The negative charge seeks out the positive charge.
Makes perfect sense.
And it's worth a quick note that even in cases where maybe a discrete, long-lived carbocation isn't definitively formed, where the positive charge is very fleeting, perhaps more like a highly polarized transition state, the regioselectivity still holds. It seems to arise from the electrophile, in this case the proton, attacking the more electron-rich carbon of the double bond anyway. Those alkyl substituents effectively increase the electron density at that particular carbon through hyperconjugation, essentially guiding the electrophile's attack to the spot that can best accommodate the developing positive charge, even if it's not a full carbocation.
So practically speaking, how does this actually work in the lab? You mentioned terminal alkenes and dissubstituted internal alkenes generally react pretty slowly with HCl in non-polar solvents.
Yes.
Not ideal for synthesis.
Right, not very efficient.
But here's where it gets really interesting, apparently. The reaction rate is greatly accelerated when you introduce silica or aluminous surfaces. These are used in non-coordinating solvents, like dichloromethane or chloroform. And these are what chemists call preparatively convenient conditions because they make the reaction much more practical, much faster.
Absolutely. You can even generate the HCl right in the reaction mixture in situ, meaning on the spot. You can use reagents like thionyl chloride or acetyl chloride to generate it. And guess what? These heterogeneous systems with the solid surface still give you that precise Markovnikov orientation. It's a fantastic way to speed things up without sacrificing that crucial regiochemical control.
Okay, so how does that surface catalysis work? What's the thinking there?
Well, the current thinking is that it involves an interaction between the silica or alumina surface, which has hydroxyl groups, and the HCl molecule. This interaction effectively facilitates the proton transfer step, making the electrophile more readily available to the alkene. It's almost like the surface acts as a tiny, highly efficient chemical matchmaker, holding the HCl in just the right way.
Interesting.
And we've also seen another clever and convenient procedure for hydrochlorination. It simply involves adding trimethylsilyl chloride to a mixture of an alkene and water. This also provides excellent yields of Markovnikov-oriented HCl addition products, often over 90%. Now, we presume HCl is generated by hydrolysis of the silyl chloride in this case.
Makes sense, reacting with water.
Right. But it's not fully clear if silicon plays any further role in the reaction itself, beyond just being a source of HCl.
Okay, this raises an important question, though. What happens if there are other nucleophiles present in the reaction mixture? Say you're running the reaction in a solvent that itself can act as a nucleophile.
Ah, yes, solvent participation. A classic issue.
Exactly. In those situations, like using acetic acid as a solvent, the solvent molecules can actually jump in and compete with the halide ion for that carbocation intermediate. A compelling example is cyclohexane reacting with HBr and acetic acid. You get mostly cyclohexylbromide, as you'd expect, maybe 85%, But you also get a noticeable percentage, like 15% of cyclohexyl acetate, or the solvent molecule added instead. That clearly illustrates the competition.
Absolutely. And furthermore, a critical consideration always with carbocations is rearrangement. If the carbocation intermediate has the ability to rearrange to form an even more stable carbocation, say, through a hydride shift, where a hydrogen atom with its electrons moves, or an alkyl shift where an entire alkyl group moves, then carbon skeleton rearrangement will occur during these electrophilic additions.
So the whole carbon backbone can change shape.
Precisely. Take T-butylethylene reacting with HCl in acetic acid. You don't just get one product. You get a mixture of both rearranged and unrearranged chloride products, along with some rearranged acetate where the solvent added after rearrangement. This is a classic example of a less stable primary carbocation rearranging, maybe via a hydride shift, to a more stable tertiary one.
Right.
Which means the product distribution becomes a complicated mix, potentially ruining your synthesis if you weren't expecting it.
Right, that makes controlling the outcome much harder. Now, let's talk about the nuance of stereochemistry, or how the atoms add in 3D space. The stereochemistry of hydrogen halide addition isn't always straightforward, is it? It depends significantly on both the specific structure of the alkene and the exact reaction conditions, like the solvent and temperature.
That's right. Generally, the addition of HBr to simple alkenes, things like cyclohexene or E and Z2-butene, proceeds predominantly by anti-addition, which means the hydrogen and the halogen add to opposite faces of the double bond. Similarly, HCl addition to 1-methylcyclopentene is entirely anti when performed in a solvent like nitromethane.
But it's not always anti.
No, and this isn't just about memorizing rules. It's about understanding the subtle dance of forces at play. What's truly fascinating is how exquisitely sensitive these reactions are to even minute changes in conditions. A seemingly minor tweak, like a few degrees in temperature or a different solvent, can completely flip the 3D outcome. Take 1,2-dimethylcyclohexene. When HCl is added at a very low temperature, say around -78 degrees C in dichloromethane, a high percentage, maybe 88% of the product results from synaddition H and Cl adding to the same face.
Wow, that's a big shift.
It is. But if you raise the temperature to 0 degrees C and use ether as the solvent instead, the product dramatically shifts. Now, 95% results from anti-addition. This highlights a really delicate balance, and we also see that syn addition is particularly common when alkenes have an aryl, like a phenyl substituent. That phenyl group can influence the stability and lifetime of the intermediate, favoring syn addition sometimes.
So why does this happen? What are the mechanistic explanations for this stereochemical control?
Well, it typically involves two main competing pathways. One is an ion pair mechanism formed immediately after the initial protonation. This pathway isn't necessarily stereospecific because the carbocation intermediate can potentially lose its original stereochemical information, for instance, by rotating around its bonds if it lives long enough. However, if that ion pair collapses very, very rapidly, the halide might still add to the same side of the alkene as the added proton, potentially leading to a preference for syn addition. But if the ion pair has a longer lifetime or dissociates completely, you'll likely get a mixture of syn and antiproducts.
Okay, that makes sense. And the other pathway?
The other pathway, often considered more common, especially for alkenes that don't form highly stable carbocations, is a termolecular mechanism. This is a bit more complex. It involves the alkene, the hydrogen halide, and a third species, often a solvent molecule or another halide ion, that acts as a nucleophile to deliver the final halide. This mechanism bypasses a discrete, long-lived carbocation and typically exhibits a strong preference for anti-addition, because the nucleophilic attack usually occurs from the opposite side of the double bond relative to where the proton added, essentially a classic backside attack.
So the deciding factor is really the carbocation stability.
Exactly. The major factor determining which mechanism, and thus which stereochemical outcome, is followed is the stability of the carbocation intermediate. If an alkene can generate a particularly stable carbocation, like a highly substituted or maybe a benzylic carbocation, it's more likely to react via the less stereospecific ion pair mechanism. It's a race, really, between how quickly the nucleophile can attack and whether the carbocation has time to rotate or dissociate.
Okay, moving on to another critical type of addition. Hydration, which is simply adding water across a double bond to form an alcohol, and related acid-catalyzed additions involving other oxygen nucleophiles. The mechanism seems similar, right? Kicks off with the addition of a proton to the double bond, forming the more substituted carbocation.
Yes, precisely. That ensures that the addition is highly regioselective and follows Markovnikov's rule. Then a water molecule acts as a nucleophile, attacks the carbocation, and a final deprotonation step yields the alcohol product. It seems straightforward on paper.
But there's a catch, as always in chemistry.
There often is. The catch here is practical limitations. Because of the strongly acidic and often vigorous conditions required for the hydration of most alkenes, this method is primarily applicable only to molecules that do not contain other acid-sensitive functional groups that might react undesirably. For example, it's occasionally used for the synthesis of tertiary alcohols, which are more stable under these conditions.
And rearrangements are still a problem.
Absolutely. Because cationic intermediates are involved, carbon skeleton rearrangements can readily occur if a more stable canthalyte cation can be formed, leading to those undesired byproducts again. This problem with harsh conditions and rearrangements directly highlights the need for better methods, which leads us perfectly into discussing oxymercuration reduction, which, as we'll see, is a much milder and more general procedure for alkene hydration. It solved a lot of these practical headaches for synthetic chemists.
Right. And beyond just water, other nucleophilic solvents, like alcohols and carboxylic acids, can also be added to double bonds using strong acids as catalysts.
Yes, exactly. This results in the formation of ethers, or esters, respectively. For example, you could take a simple alkene like isobutylene and react it with methanol catalyzed by a strong acid like HBF4, and you'll get methyl T-butyl ether, an important gasoline additive. Or propene with acetic acid, again with an acid catalyst, yields isopropyl acetate and ester.
And you mentioned trifluoroacetic acid, TFA.
TFA is interesting because it's a strong enough acid to react with alkenes under relatively mild conditions, and the addition still remains regioselective according to Markovnikov's rule. Plus, here's a neat fact. Wing strain can significantly enhance alkene reactivity. Norborne, for instance, a bicyclic alkene with considerable built-in strain from its bridge structure, undergoes rapid addition of TFA even at 0 degrees C. That strain makes it much more eager to react than a typical unstrained alkene.
Okay, so that leads us nicely to oxymercuration reduction. You mentioned this is milder and avoids rearrangement.
Yes, it's a real workhorse in organic synthesis for precisely those reasons. While protonation initiates many additions, the electrophile can also be a metal cation. And here, the mercuric ion, HgO, is the electrophile in several synthetically valuable procedures. The most commonly used reagent is mercuric acetate, HgOAc2, but more reactive alternatives like mercuric trifluoroacetate or nitrate salts can be preferable in specific applications.
And the mechanism involves this mercurinium ion.
That's the generally accepted picture. The mechanism depicts a mercurinium ion as a key intermediate. What's fascinating here is that such species can actually be detected by physical measurements, like NMR, when alkenes react with mercuric ions in non-nucleophilic solvents. So we have good evidence for them. This CAF cation can exist predominantly as a bridged structure similar to a bromonium ion, or perhaps a more open one, depending on the specific alkene structure. It's likely a spectrum of possibilities.
Okay, so the mercury bridges and then the nucleophile attacks.
Exactly. The addition is completed by the attack of a nucleophile at the more substituted carbon of the alkene. This nucleophilic capture step is usually the rate-determining and product-controlling step. After this addition, the mercury is typically removed reductively using sodium borohydride, NaBH4.
And the net result.
The net result is the efficient and regioselective addition of hydrogen and the nucleophile across the alkene. What's crucial is that the regioselectivity is excellent and, in the same sense, Markovnikov orientation, as observed for proton-initiated additions. But critically, without the problematic rearrangements or harsh acidic conditions.
And you mentioned it's versatile with nucleophiles.
Incredibly versatile. Water is common, leading to alcohols.
Yep.
But also alcohols give ethers, carboxylate ions give esters, hydroperoxides give peroxides, amines give substituted amines, and even nitriles can participate, yielding amides via something called the Ritter reaction after hydrolysis. This makes oxymercuration incredibly powerful for introducing a wide range of functional groups.
Now, that demercuration step with sodium borohydride, you said it's not straightforward ionic chemistry.
No, it's actually quite fascinating. The reductive replacement of mercury using NaDH4 is not a simple ionic process. It's generally accepted to be a free radical chain reaction. This involves an intermediate called a mercuric hydride, RHGIIH. There's strong evidence for this. For example, the reaction can be completely diverted by oxygen, which is an incredibly efficient radical scavenger. In the presence of oxygen, the mercury is replaced by a hydroxy group instead of hydrogen.
Whoa, so you get an alcohol instead of just removing the mercury.
Exactly, which is a neat synthetic trick if you want to introduce an OH group selectively. Also, the formation of cyclic products, when certain mercury compounds containing appropriately placed double bonds are reduced with NaBH4, is highly characteristic of reactions involving free radicals. The radical cyclizes onto the double bond before being reduced. And interestingly, if oxygen is present, no cyclic product forms, indicating oxygen traps the radical faster than it can cyclize. Other radical-reducing agents, like triene-butyl anhydride, can also be used, further supporting this radical pathway.
But you mentioned there's another way.
Right, this is a tale of two mechanisms. An alternative demercuration reagent is sodium amalgam. That's an alloy of sodium and mercury used in a product solvent. Here, the evidence suggests that free radicals are not involved. Instead, the mercury is replaced with retention of configuration at the carbon center. So, depending on your reducing agent, you get a completely different mechanistic pathway and stereochemical outcome. It's quite remarkable.
Okay, so what about the stereochemistry of the initial oxymercuration step itself, before the reduction?
Good question. For conformationally biased cyclic alkanes, like 4-T-butyl-cyclohexene, where the bulky T-butyl group locks the ring conformation, the reaction gives exclusively the product of anti-addition. This is perfectly consistent with the intermediacy of a bridged mercurinium ion, where the nucleophile is forced to attack from the opposite face, like we saw with bromonium ions.
Makes sense. The bridge blocks one side.
Right. But in contrast, norborne, with its unique strained bicyclic structure, reacts by synaddition. This is believed to occur through an internal transfer of the nucleophile, perhaps involving the mercury assisting from the same face. It illustrates a unique aspect of its geometry.
And how does alkene structure affect reactivity?
The reactivity of different alkenes toward mercuration varies considerably, influenced by a mix of steric and electronic factors. Generally, terminal double bonds are more reactive than internal ones, which makes sense sterically. However, dis-substituted terminal alkenes are more reactive than monosubstituted ones, which is what we'd expect electronically for an electrophilic attack. More electron donation stabilizes the intermediate. These differences can even be large enough to achieve selectivity with certain dienes, where you can target just one of the double bonds if their reactivities are different enough.
And can neighboring groups influence the outcome? You mentioned that earlier.
Yes. We've seen fascinating diastereoselectivity. That's selectivity between different spatial arrangements that aren't mere images in the oxymercuration of alkenes that have nearby oxygen substituents. Specifically, terminal allylic alcohols show a preference for the formation of anti-2-3 diols. This result can often be explained by a steric preference for one conformation over another in the transition state, where the hydroxy group effectively directs the approach of the mercuric ion. It's almost as if the hydroxy group is holding the door open for the mercuric ion to approach from a specific side. And the selectivity often increases with the size of the substituent on the allylic alcohol, highlighting that steric bulk can be a powerful controlling element.
Does this steering effect work with other groups besides OH?
It does. Allylic silyloxy groups, that's an oxygen attached to a silicon protecting group, also show directing effects. These reactions show complete regioselectivity for 1,3 oxygen substitution. For example, Z-isomers of certain allylic ethers show modest stereoselectivity, but interestingly, the corresponding ethers show no stereoselectivity in similar reactions. However, highly substituted allylic silyloxy ethers show good stereoselectivity. This is again consistent with the silyloxy substituent directing the reaction through a sterically favored conformation of the reactant.
What about acetate groups?
With acetoxy derivatives, that's an acetate group. The 2-3 isomer is preferred. And what's fascinating here is that this occurs as a result of direct nucleophilic participation by the carbonyl oxygen of the acetoxy group itself. It forms a temporary cyclic intermediate that then opens to give the syn product. So the molecule is essentially helping itself cyclize in a specific way.
That's really clever.
It is. Even polar substituents further away can exert a directing effect. For example, cyclohexanol shows high regioselectivity, but surprisingly low stereoselectivity for the overall product, indicating that factors other than direct hydroxy coordination must be involved. And computational studies on substituted norbornes even found that polar effects of electron withdrawing groups favor mercuration at the carbon closer to the substituent. This was attributed to a favorable polar effect stabilizing the developing negative charge on the mercuriated carbon during the electrophilic attack. It's complex.
Okay, let's bring this to life with some examples. You mentioned alcohol formation.
Yes. Several examples clearly illustrate the Markovnikov orientation under typical oxymercuration reduction conditions, leading reliably to alcohol formation where the OH group is on the more substituted carbon. We also see examples of high exoselectivity in bicyclic systems, where the incoming group adds preferentially to the outside face of the ring structure, consistent with steric approach control on perhaps a weakly bridged or even open mercurinium ion. And the absence of rearrangement in these examples is key. It tells us the intermediate isn't a freely rearranging carbocation like in acid-catalyzed hydration.
And forming ethers.
Straightforward. Examples demonstrate the formation of ethers when alcohols are used as solvents to capture that mercurinium ion intermediate. You just swap water for an alcohol.
And amides.
Yes. Another example highlights the formation of an amide product when estanitrile is employed as the solvent and nucleophile, likely going through that Ritter reaction intermediate we mentioned.
And beyond that,
the examples further broaden our perspective by showing the successful use of other diverse nucleophiles, like hydroperoxides to form organic peroxides, and primary amines to form secondary amines, all by capturing that key mercurinium ion intermediate. These illustrations really underscore the truly broad synthetic utility of oxymercuration reduction. It shows how one core strategy can be adapted to build many different molecular architectures cleanly and predictably.
okay, let's switch gears now to the addition of halogens to alchemies. Bromination, chlorination, iodination, and fluorination. This is a really fundamental reaction in organic chemistry. Right?
Absolutely. Very general. Bromination of simple alkanes, for instance, is extremely fast, almost instantaneous sometimes. And since halogenation involves an electrophilic attack, substituents on the double bond that increase electron density, those electron-donating groups, will naturally increase the rate of reaction.
Yeah.
Electron-withdrawing groups, as you'd expect, will slow things down.
And the stereochemistry here is pretty revealing.
Very revealing. Considerable insight into the mechanism of halogen addition has come from studies of its stereochemistry. Most simple alkanes add bromine in a stereospecific manner, giving exclusively the product of anti-addition. This means the two halogen atoms add to opposite faces of the double bond. Think of classic examples like Z2-butene or E2-butene, where the specific stereochemistry of the starting material dictates the specific stereochemistry of the dibromide product.
And the explanation for that involves bridging.
Exactly. The elegant explanation for this observed anti-stereospecificity is the formation of cyclic, positively charged polonium ion intermediates, specifically bromonium ions for bromination or chloronium ions for chlorination. This bridging by the halogen atom across a double bond prevents rotation about the original carbon-carbon bond of the alkene. It locks the geometry. Subsequent nucleophilic opening of this halonium ion by a halide ion, typically attacking from the backside, opposite to the bridging halogen, leads directly and cleanly to the observed anti-addition product.
And we know these halonium ions are real.
Oh yes, it's not just a convenient hypothesis. There's direct evidence for the existence of bromonium ions from NMR measurements, which can essentially see these short-lived species under the right conditions. And what's even more compelling is that a bromonium ion salt has actually been isolated and structurally characterized from the reaction of bromine with a very hindered alkene called adamantyladenyadenantane. That's about as concrete proof as you can get in chemistry for a reactive intermediate.
But like Markovnikov's rule, there are exceptions to this anti-addition rule.
Yes, chemistry loves its exceptions. A substantial amount of syn addition, where halogens add to the same face, is observed for alkenes with phenyl substituents. Things like Z1-phenylpropene and cis-stelbene can give significant amounts, sometimes up to 90% syn addition, especially in polar solvents.
Why the phenyl group?
The common feature is that phenyl group right on the double bond. The phenyl group diminishes the strength of the bromine bridging. Why? Because the phenyl group can effectively stabilize the developing positive charge on the adjacent carbon center through resonance. It can share the burden of the positive charge. This leads to a weakly bridge structure existing in equilibrium with a more open benzylic cation. This open, less constrained intermediate allows for rotation around the CC bond and allows the nucleophile, the halide, to attack from either face, accounting for the loss in stereospecificity and the increased syn addition. This diminished stereospecificity is quite similar, mechanistically, to what we observed for hydrogen halide addition to phenyl-substituted alkanes. The phenyl group changes the nature of the intermediate.
And chlorination follows similar patterns, but maybe less pronounced.
Pretty much. While chlorination of simple aliphatic alkanes usually gives anti-addition, syn addition is often dominant for phenyl-substituted alkanes for the same reasons. These results also reflect differing extents of bridging in the chloronium ion intermediates. With unconjugated alkanes, you get strong bridging and high anti-stereospecificity. Phenyl substitution leads to more cationic character at the benzylic site, less effective bridging, and thus more syn addition. Furthermore, just based on atomic properties, chlorine, being smaller and less polarizable than bromine, is generally not as effective as bromine in forming strong bridges for any given alkene. Therefore, bromination generally yields a higher degree of anti-addition than chlorination, all other factors being equal. Bromine is just better at forming that strong bridge.
Are there other side reactions that hint at carbocations being involved?
Definitely. These reactions aren't always perfectly clean additions, and some side reactions clearly indicate the involvement of carbocation intermediates, just like we saw with hydrogen halides. For instance, chlorination can sometimes be accompanied by proton elimination directly from a cationic intermediate, especially with branched alkenes. This gives elimination products where a double bond is reformed adjacent to the new chlorine atom. And again, in systems predisposed to skeletal rearrangements where a more stable carbocation can form via migration of an alkyl or hydride group, these rearrangements are indeed observed during chlorination, leading to complex product mixtures.
And solvent competition is also a factor here.
Yes, just as with HX additions, nucleophilic solvents can compete with the halide ion for the cationic intermediate during halogenation. For example, the bromination of styrene and acetic acid leads to significant amounts of an acetoxybromo derivative alongside the expected dibromide. What's interesting is that the acetoxy group is introduced exclusively at the benzylic carbon, which again aligns with an intermediate that is either a weakly bridged species or an open benzylic cation where the positive charge is localized. And adding extra bromide salts to the reaction mixture is a clever trick chemists use to diminish the amount of acetoxy compound formed, by simply outcompeting the solvent with a higher concentration of bromide ion. Similarly, chlorination in nucleophilic solvents like methanol can lead to solvent incorporation products where a methoxy group ends up in your molecule.
Now, you mentioned bromohydrins earlier with mercury, but they also form directly during bromination in water.
Yes, and from a synthetic perspective, the participation of water in brominations, leading to the formation of bromohydrins, molecules with a bromine and a hydroxyl group on adjacent carbons, is one of the most important examples of nucleophilic capture of the intermediate by a solvent. It's a very useful reaction. To maximize the introduction of water, and thus bromohydrin formation, it's crucial to keep the concentration of the competing bromide ion as low as possible. Otherwise, you just get dibromide.
How do you do that?
One highly effective method for achieving this is to use N-bromosuccinimide, or NBS, as the brominating reagent instead of Br2. High yields of bromohydrins are obtained by using NBS and aqueous DMSO, which is dimethyl sulfoxide. The reaction proceeds with stereospecific anti-addition consistent with a bromonium ion intermediate. What's fascinating is the role of DMSO. The reactions carried out in DMSO are thought to involve nucleophilic attack by the sulfoxide oxygen itself first. The resulting alkoxysulfonium ion intermediate then reacts with water to give the bromohydrin. This indirect route helps manage bromide concentration and favors water addition. It's a neat mechanistic detail.
And the regioselectivity is still Markovnikov-like.
Yes, in accordance with Markovnikov's rule for these types of reactions, the hydroxy group, OH, is introduced at the carbon, best able to support a positive charge, the more substituted carbon, while the bromine attaches to the less substituted carbon. For example, if you take 2003-3-trenethyl-1-butene and react it with NBS and aqueous DMSO, you'll predictably get the tertiary alcohol product with the bromine on the primary carbon. Very reliable.
Can internal groups participate too?
Absolutely. The participation of internal sulfoxy groups can be cleverly used to control stereochemistry in acyclic systems, leading to specific 3D arrangements through intramolecular capture. And a practical procedure for preparing both bromohydrins and iodohydrins involves generating the hipolydous acid, HOBr or HOI, in situ from reagents like sodium bromate or sodium periodate by reduction with bisulfite. These reactions show the same regioselectivity and stereospecificity as other reactions proceeding through halonium ion intermediates, offering alternative, convenient synthetic routes.
Okay, now let's tackle fluorine. You said it's tricky.
Very tricky. Because of its extremely high reactivity, elemental fluorine F2 reactions require special precautions, like specialized equipment and handling procedures, making its use somewhat specialized in the lab. And mechanistically, the addition of fluorine to Z and E1-propanylbenzene is not stereospecific, though synaddition is somewhat favored. This result is consistent with the formation of a more open cationic intermediate, rather than a strongly bridged fluoronium ion. Fluorine is just too small and not polarizable enough to bridge effectively.
So it behaves more like a simple carbocation reaction.
Essentially, yes. And in nucleophilic solvents like methanol, the solvent incorporation product is readily formed, as you'd expect for a cationic intermediate that's looking for any available electron-rich species. These observations are consistent with the expectation that fluorine would not be an effective bridging atom compared to its heavier halogen cousins, bromine or chlorine.
Are there better ways to add fluorine?
Yes, chemists have developed alternative reagents. Things like CF3OF and CH3CO2F are known to transfer an electrophilic fluorine to double bonds, likely involving an ion pair that then collapses to form the addition product. The stability of these hypofluorides is improved in derivatives with electron-withdrawing substituents, making them safer and easier to handle. Furthermore, various storable fluorinating agents have been developed and used, including N-fluoropyridinium salts. Their reactivity can even be tuned by varying substituents on the pyridine ring, giving chemists precise control over the fluorination process. In nucleophilic solvents, these reagents yield addition products, but in non-nucleophilic solvents, alkanes can undergo substitution products resulting from deprotonation of a carbocation intermediate instead.
And iodine. You mentioned it's sensitive.
Right. Addition of iodine I2 to alkenes can be accomplished by a photochemically initiated reaction using light, but the resulting diodo compounds are often very sensitive to light themselves and tend to decompose, so they are seldom used directly in syntheses. They just don't stick around long enough.
So, elemental halogens aren't the only game in town for adding halogens electrophilically.
Not at all. For specific synthetic purposes, other positive halogen compounds, where the halogen acts like it has a positive charge, may be preferable as electrophiles. We already talked about the utility of N-bromosuccinimide, NBS, in forming bromohydrins. Both N-chlorosuccinimide, NCS, and NBS transfer electrophilic halogen. Crucially, the succinimide anion that leaves is subsequently protonated to yield succinimide, which is a very weak nucleophile. It's a huge advantage. These reagents thus favor nucleophilic additions by the solvent or intermolecular cyclization reactions, because there is no strong competition from a halide anion trying to attack the intermediate. It lets the desired reaction win.
Are there other sources with tuned reactivity?
Yes, several compounds are useful for specific purposes. Things like pyridinium hydrotribromide, benzylrhomodium tribromide, and dioxin-bromine are examples of bromine complexes where the bromine's reactivity is somewhat attenuated or lessened. This leads to increased selectivity in reactions. It's like putting the brakes on a super-fast reaction to gain more control over the outcome. 2,4-canny-4,6-tetrabromocyclohexadanone is another very mild and selective source of electrophilic bromine. The leaving group in this case is the stable 204-count-6-tribromophenoxide ion. And for iodine, electrophilic iodine regions are used extensively in iodocyclization, that powerful ring-forming reaction we'll discuss more soon. Salts of pyridine complexes with ibosu, like bis-pyridinium iodonium tetrafluoroborate and bis-collidine iodonium hexasorphosphate, have proven especially effective for these cyclizations, offering high reactivity and efficiency.
Okay, let's broaden our view slightly to other electrophilic reagents beyond just the typical halogens. You're saying many other halogen-containing compounds react similarly.
Yes. They react with alkenes to yield addition products through mechanisms remarkably similar to halogenation itself. They typically form a complex with the alkene, transfer a halogen atom, or something halogen-like, to the alkene, and generate a bridged cationic intermediate. This intermediate can be a symmetrical halonium ion or an unsymmetrically bridged species, depending on how well the reacting carbon atoms can accommodate positive charge.
And the regiochemistry and stereochemistry follow the same patterns.
Generally, yes. The direction of opening of the bridged intermediate is usually governed by electronic factors. The addition is completed by the attack of the nucleophile at the more positive carbon atom of the bridged intermediate. Therefore, the regiochemistry of addition generally follows Markovnikov's rule, and the stereochemistry of addition is typically anti due to the involvement of the bridged halonium intermediate, which forces the nucleophile to attack from the opposite face. It's a very consistent pattern driven by that bridge structure.
What are some examples of these other electrophiles?
Well, we see various interesting examples. There are additions where iodine acts as the electrophile, but various pseudohalide anions, things like isocyanate, NCO-azide, N3, and thiocyanate, SCN, serve as the nucleophiles. This really highlights the versatility of the halonium ion, intermediate in capturing diffuse nucleophiles beyond just simple halides. You can build in nitrogen or sulfur functionality this way.
What about thiocyanate itself as an electrophile?
Good question. For reagents like thiocyanogen chloride, ClSCN, and thiocyanogen SCN2, the formal electrophile is effectively amiol plus NCS, or SCN plus male. The presumed intermediate is a cyanothiorinium ion, a sulfur-bridged species. What's fascinating here is that the thiocyanate anion, SCN, is an amidant nucleophile, meaning it has two potential sites for nucleophilic attack, either the carbon or the nitrogen. Depending on the specific reaction conditions, both carbon-sulfur and carbon-nitrogen bond formation can be observed, offering a choice in connectivity.
Interesting. And NO plus me.
Yes, for nitrosyl chloride, NOCl, and nitrosyl formate, NOOCOH, the electrophile is the nitrosonium ion, NO+. The initially formed nitroso compounds, which have an NOO group, can then dimerize or often isomerize to form the more stable oximes, which have a CNOH group.
Now let's talk about electrophilic sulfur and selenium reagents. This involves sulfonylation and selenylation.
Exactly. Compounds containing divalent sulfur, S, or selenium, C atoms, bound to more electronegative elements like chlorine and RSCl or RCCl, readily react with alkanes to form addition products. The mechanism is analogous to halogenation, involving the formation of bridged cationic intermediates, the radium ions for sulfur, or selenuranium ions for selenium.
And what's the main synthetic value here?
A key aspect of these reactions for synthetic chemists is that the sulfur or selenium substituent introduced during the addition is frequently removed later by an elimination reaction. This makes these additions incredibly valuable for indirectly introducing unsaturation or double bonds at specific positions in molecules. It's like a temporary handle you attach to guide a later transformation, often oxidation followed by elimination, to form a double bond precisely where the S or C was.
Are there many different S and C reagents?
Oh yes, a whole range have been developed for sulfonylation. Aryl and alkyl sulfonyl chlorides, RSCl, are highly reactive. Dimethyl methylthiosulfonium fluoroborate is useful because dimethyl sulfide is a good leaving group, allowing capture by other nucleophiles like solvents or anions, acetate cyanide. Sulfonamides typically require a Lewis acid catalyst to get them going. And there's a clever application of something called the Pummerer rearrangement for the in situ generation of a sulfonylation region. Here, sulfoxides react with acid anhydrides, like trifluoroacetic anhydride, to generate sulfonium salts. If a teal group is present, fragmentation occurs, producing a highly reactive sulfonylium ion, Rs+.
And for selenium boration, similar variety.
Very similar. A diverse set of selenylation reagents exists. Aryl chlorides and bromides like VHE2, VHA-Ber are common. Selenium salts with non-nucleophilic cancerians offer high reactivity. Selenyl trifluoroacetates, sulfates, and sulfonates are also effective. Diphenyl diselenide, PHAC2, a readily available starting material, can be activated by various oxidation reagents like ammonium persulfate or even phenyliodine diacetate to transfer electrophilic phenylselenidylylium ions. And phenylselenidyl, often called NSP, is a particularly useful synthetic reagent due to the non-nucleophilicity of the phenylamido leaving group, minimizing side reactions, similar to NBS and NCS. And there are even hindered selenyl bromides, specifically useful for promoting selenyl cyclizations, which we'll get to.
Can these capture other nucleophiles too?
Absolutely. Selenylation reactions can also be designed such that another nucleophilic component of the reaction mixture, besides the cancerian from the reagent, captures the selenium-bridged ion. For example, combining phenylselenyl and trimethylsilazide generates azidoselenides, putting both N3 and Ceph groups across the double bond. Similarly, phenylselenyl chloride used with silver tetrafluoroborate and ethyl carbamate yields agarmidoselenides. What's interesting is that in the absence of stronger nucleophiles, the solvent itself can be captured, as seen in selenide lamidation reactions carried out in acetonitrile. And if phenylselenyl chloride reactions are conducted in aqueous acetonitrile solution, hydroxylenidides are formed as a result of solvolysis reaction with the water in the solvent.
What do we know about the mechanism of sulfonyl halide additions?
Mechanistic studies have been most thorough with the sulfonyl halides. They show moderate sensitivity to alkene structure, with electron-releasing groups on the alkene accelerating the reaction, as expected for an electrophile. The regioselectivity, however, can vary. It can proceed in either the Markovnikov or sometimes the anti-Markovnikov sense.
Anti-Markovnikov, why would that happen?
It's a bit counterintuitive for an electrophilic addition, right? But this variation can be understood by focusing on the nature of the sulfur-bridged intermediate. This intermediate can range from a highly charged, more sulfonium ion-like structure, like a halogenium ion, to a less electrophilic, more covalent structure, sometimes called a chlorosulfuran. Compared to a bromonium ion, the carbon-sulfur bonds in these intermediates are generally stronger, and the transition state for nucleophilic addition is reached later in the reaction coordinate. This means that steric interactions that influence the accessibility for the incoming nucleophile become a more important factor in determining the direction of addition, sometimes overriding electronics.
So if the intermediate is stable and sterics matter more,
Exactly. For reactions involving phenyl sulfonyl chloride or methyl sulfonyl chloride, the intermediate is fairly stable, and the ease of approach by the nucleophile, usually the chloride counterion, is the major factor determining the direction of ring opening. In these specific cases, the product often shows the anti-Markovnikov orientation. The nucleophile attacks the less hindered carbon, even if it's less positively charged. For example, CH2, CH3 reacting with CH3SCS yields mostly ClCH2CH2CH3, illustrating the anti-Markovnikov placement of the chlorine on the less substituted CH2 group.
and selenoid halides. Anything tricky there?
With selenoid halides, terminal alkenes generally react with standard Markovnikov's regioselectivity. However, an important caveat, something to really watch out for in the lab, is that the initial iconomethyl and halide addition products can readily rearrange to their isomeric products. This spontaneous rearrangement can complicate synthetic planning if you're not aware of it, potentially leading to unexpected mixtures if you let the reaction sit too long or heat it up.
Okay, let's connect this idea of intramolecular reactions. This is where the molecule reacts with itself, right? Leading to cyclization.
Exactly. Here's where we see the real beauty and power of intramolecularity. When unsaturated reactants, those with double or triple bonds, also contain substituents that can function as nucleophiles within the same molecule, electrophilic reagents frequently bring about cyclizations. A new ring is formed.
And what kind of internal nucleophiles work?
Oh, quite a variety. Common groups that can act as internal nucleophiles include carboxyl, COOH, and carboxylate, COO, hydroxyl, OH, amino, NHR, and amido, KONHR, as well as carbonyl oxygen, CO, and even thiol, SH. There have been numerous examples of synthetic application of these electrophilic cyclizations. They are incredibly powerful tools for building complex cyclic structures found everywhere from natural products to synthetic drugs. They are a cornerstone of complex molecule synthesis.
Is there a preference for certain ring sizes?
There's a general observed ring size preference in these reactions. Usually 5-membered rings are favored over 6-membered rings, which are generally favored over 3-membered and 4-membered rings, so typically 5, 6, 3, 4. But it's important to note, as always, there are exceptions. Chemistry keeps us on our toes.
And what determines these preferences and the stereochemistry?
Both the ring size preference and the stereoselectivity of these cyclization reactions can typically be traced back to the precise structural and conformational features of the cyclization transition state. This is crucial for predicting outcomes. The molecule essentially has to twist and align itself just right for the ring to close efficiently and selectively.
This sounds like where Baldwin's rules come in handy.
Precisely. Baldwin's rules were developed to understand and predict the feasibility and preferred modes of these cyclization reactions. He classified cyclizations as exo or endo, referring to whether the new bond forms outside or inside the ring, being closed, and as tet, trig, and dig, referring to the hybridization sp3, sp2, sp of the carbon atom undergoing attack. The cyclizations are also designated by the size of the ring being formed, for example, a 5-exotrig cyclization.
So the rules predict which mode, exo or endo, is preferred for a given ring size.
Yes. Baldwin's rules highlight that for any given separation, N, representing the number of atoms connected to the electrophilic and nucleophilic centers, either an exo or endo mode of cyclization is usually preferred based on geometry. For cyclizations at trigonal sp2 centers, which is common with alkenes, the preferences are quite strong. 5-endo is much preferred over 4-exo for N2, 5-exo is preferred over 6-endo for N3, and 6-exo is strongly preferred over 7-endo for N4. These relationships are determined by the preferred trajectory, essentially the optimal angle of approach of the nucleophile to the electrophilic center. Some angles are just easier to achieve geometrically than others.
And substituents can influence this.
Absolutely. Substituents on the molecule can profoundly affect the transition state structure by establishing preferred conformation, essentially pre-organizing the molecule for cyclization, and by exerting electronic or steric effects that might favor one pathway over another. The most common and synthetically useful cases involve the formation of 5- and 6-membered rings. Again, the key electrophiles initiating these reactions are things like Br plus I plus Rs plus Rse plus I or Hg2 plus Ra, and the internal groups acting as nucleophiles are often CO2, OH, CO, NHR, or SH. This is a very versatile toolkit for ring construction.
Let's start with halocyclization then, where a halogen kicks off the ring closure.
Right. Brominating and iodinating reagents are particularly effective at inducing cyclization in alkenes that possess a nucleophilic group appropriately situated to allow for the formation of 5, 6, and in some special cases, even 7-membered rings. While hydroxyl and carboxylate groups are the most common internal nucleophiles in halocyclization, the reaction is feasible for any nucleophilic group that is compatible with the electrophilic halogen source. For instance, amides and carbonyls can react at either their oxygen or nitrogen atoms, depending on which atom is closer or better positioned geometrically to attack the halonium ion intermediate. Sulfonamides are also viable nitrogen nucleophiles. And even carbonyl oxygens can act as nucleophiles, often yielding stable products through a subsequent deprotonation step.
And the intermolecular reaction usually wins out over intermolecular addition.
Yes, intramolecular reactions usually significantly dominate over competing intermolecular addition reactions, especially for favorable ring sizes like 5 and 6. This is a powerful synthetic advantage because the reaction is much more efficient when the two reacting partners are already tethered together in the same molecule. We even have calculations, semi-empirical AM1 calculations, that have found the intramolecular transition state to be more stable by nearly 4 kilocalmol compared to a comparable intermolecular reaction. That's a significant energetic preference. What's fascinating about this calculated intramolecular transition state for EpiR plus and 4-pent-1-ol is that it's quite product-like, meaning the new CO bond is already substantially formed in the transition state. The bromonium ion bridging is unsymmetrical and relatively weak here.
Are there specialized reagents for this?
In addition to the more typical bromination reagents, a unique procedure for bromolactonization, forming a lactone ring with a bromine attached, involves the combination of trimethylsilbromide, TMSBr, a tertiary amine base, and DMSO. Also, certain sulfate derivatives, like 3-phenylprop-2-anyl sulfates, undergo cyclization both stereospecifically and with Markovnikov radiochemical control, representing endo-6 cyclizations.
Now, iodolactonization seems particularly important.
It is. Iodolactonization is a highly studied and incredibly crucial reaction in synthesis. Iodine is an exceptionally good electrophile for inducing intramolecular nucleophilic addition to alkanes. The reaction of iodine, I2, with carboxylic acids containing carbon double bonds, positioned to allow for intramolecular reaction, consistently results in the formation of iodolactones. The reaction shows a pronounced preference for forming 5-membered rings over 6-membered rings, and crucially, it proceeds as a stereospecific anti-addition when carried out under basic conditions, for example, using sodium bicarbonate.
You mentioned kinetic versus thermodynamic control here.
Yes, that's a key point. The anti-addition observed under basic conditions is a kinetically controlled process. This means it's simply the fastest reaction pathway available, resulting from the irreversible backside opening of an iodonium ion intermediate by the carboxylate nucleophile. Once it forms, it stays that way. However, seminal work by Bartlett and Go workers showed that if the reaction is performed under acidic conditions, where acid-catalyzed equilibration can occur, meaning the reaction can reverse and try again, the more thermodynamically stable trans product is obtained eventually, the product where the groups are further apart and less sterically crowded. This highlights the delicate balance between kinetic and thermodynamic control in determining stereochemical outcomes. Reaction conditions can choose either the fastest path or the path to the most stable destination.
And conformation plays a big role under kinetic conditions.
Absolutely. Under kinetic conditions, iodolactonization beautifully reflects the reactant's preferred conformation, its 3D shape. Several cases powerfully illustrate how the stereoselectivity of iodolactonization can be directly related to the preferred conformation of the starting material. For example, high stereoselectivity observed for a specific dialkylcuprates acid corresponds to the spatial proximity of the carboxylic group to one of the two double bonds in its lowest energy reactant conformation. It reacts with the closer one. Similarly, with other reactants, conformational preference strongly dictates the selectivity between competing internal nucleophiles, like a carboxylate, versus hydroxyl group, if one is positioned much better than the other. This conformational preference can even extend to cases where a typically less nucleophilic group, like an ester, cyclizes preferentially over a more nucleophilic hydroxyl group if the ester happens to be in the conformationally favored position for ring closure. Geometry wins.
But inherent reactivity can sometimes override conformation.
Exactly. On the other hand, when the competition is between a monosubstituted and a dissubstituted double bond within the same molecule, the inherent reactivity difference between the two double bonds, so the dissubstituted being inherently more reactive towards electrophiles because it's more electron-rich, overcomes any subtle reactant conformational preferences. The reaction will selectively occur at the more reactive double bond, regardless of which one might seem closer in a particular conformation. So Sometimes inherent chemical reactivity trumps the way the molecule happens to be folded at that moment.
What other groups can cyclize like this?
Several others. T-butyl carbonate esters can cyclize to form dialkylates. Lithium salts of carbonate monoesters can also be cyclized. Enhanced stereoselectivity has been found using IBR, iodine monobromide, which reacts at a lower temperature. Comparing examples, IBR can improve the cis-trans ratio dramatically for T-butyl carbonate cyclization when conducted at -80 degrees C, and this ratio was also found to be solvent-dependent, with toluene being optimal. Other reagent systems that generate electrophilic iodine, such as potassium iodide combined with potassium persulfate, oxone, can also be used effectively for iodophoscyclization.
How does bromocyclization compare to iodocyclization?
Analogous cyclization reactions are indeed induced by brominating reagents, but they generally tend to be less selective than the iodocyclizations. This is usually attributed to bromonium ion intermediates being much more reactive and consequently less selective in their subsequent reactions. They react so fast, they don't always have time to be as picky about the stereochemistry or regiochemistry compared to the less reactive iodonium ions.
What's the synthetic utility of these halocyclization products?
The products of iodocyclization, iodolactones, iodoethers, etc., are synthetically highly valuable. They possess a potentially nucleophilic oxygen substituent right next to the iodide atom. This structural feature makes them incredibly useful intermediates in stereospecific syntheses of epoxides by treating with base and diols by subsequent reactions. They allow for precise control of 3D structure in subsequent steps.
Can you form simple ethers like tetrahydrofurans this way?
Absolutely. Positive halogen reagents, especially iodine sources, can effectively cyclize pentoxyalkenes to form tetrahydrofuran, 5-membered rings, and tetrahydroperin, 6-membered rings, derivatives, respectively. Specifically, iodocyclization of homoallylic alcohols, those with an OH group 4 carbons away from the double bond, generates 3 iodotetrahydrofurans when performed in anhydrous acetonitrile. These reactions are highly stereospecific. E alcohols yield the trans product, and Z isomers yield the cis product, reflecting the anti-addition mechanism. Mechanistically, these are usually endo-5 cyclizations, which are preferred over exo-4 reactions according to Baldwin's rules. With corresponding secondary alcohols, the preferred cyclization occurs via conformation that places the reacting substituents into pseudo-equatorial orientation to minimize steric strain. Related ethers like OTBS or obenzyl ethers can also cyclize, often with the intriguing outcome of losing the ether protecting group during the process, which can be a useful synthetic shortcut.
And nitrogen groups like amides can participate too.
Yes, other nucleophilic functional groups can participate. Amides, for instance, usually react at their oxygen atom first, generating intermediate iminolactones that are subsequently hydrolyzed by water to the final lactones during workup. What's particularly exciting is that the use of a chiral amide, derived from a chiral auxiliary, can promote enantioselective cyclization. The preference for one enantiomer over the other in the transition state is influenced by the avoidance of A13 strain between specific groups in the chiral auxiliary and the forming ring. Lactams, which are cyclic amides, can be obtained by cyclization of O-N-trimethylsilylimidates. imidates. In contrast to amides, where oxygen is usually more nucleophilic, silylimidates are more nucleophilic at their nitrogen atom, leading to direct N-cyclization, another powerful way to build nitrogen-containing rings.
Maybe walk us through a few highlights from the examples of these halocyclizations.
Sure. One example uses NBS, demonstrating the classic anti-stereospecificity and the preference for forming 5-membered rings. Another shows a straightforward 5-exo bromocyclization. We see the formation of a lactone in an acyclic system, carried out under conditions designed to favor the thermodynamically more stable trans isomer. Typical iodolactonization conditions using iodine and bicarbonate again show anti-stereoselectivity and the preference for 5-membered rings. But 6-membered lactones can also form, still with anti-stereospecificity.
The carbonate example sounded interesting.
They are. One shows the cyclization of a T-butyl carbonate ester. The selectivity observed between 2 potential double bonds in the molecule is a direct result of the relative proximity of the nucleophilic carbonate group to one of those double bonds in the preferred conformation, guiding the reaction. A related reaction using IBR at much lower temperatures significantly improved the cis-trans ratio to nearly 26.1, and the ratio is also solvent-dependent, with toluene being best. This really shows the power of optimizing conditions. We also see a variation using a lithium carbonate as the nucleophile.
What about hydroxyl groups as nucleophiles?
Yes, several examples involve hydroxy groups serving as nucleophiles. One is a 6-endo iodocyclization. In another, a primary hydroxy group effectively serves as the nucleophile. There's even an intricate cyclization involving a hydroxy group forming a unique bridged bicyclic ether structure, and another highlighting a rather unusual 5-endo cyclization pathway. One interesting case shows cyclization occurring with the simultaneous loss of a common nitrogen-protecting group, the amides group. The transition state conformation here is determined by placing a metal group in a preferred pseudo-equatorial position.
And the lactam formation.
Right. That involves the formation of a lactam through the cyclization of a beast trimethylsilylimidate. What's interesting is that the stereoselectivity in this reaction closely parallels that observed in iodolactonization, suggesting similar controlling factors.
And these are used in longer syntheses.
Absolutely. Several examples illustrate the power of iodocyclization as the strategic step within more complex multi-step syntheses. For instance, iodolactonization followed by elimination of HI from the resulting bicyclic lactone to install a double bond. Another shows a sensitive cyclic peroxide group remained unaffected by the standard iodolactonization conditions and subsequent reduction, showcasing useful functional group compatibility. In another, the primary iodo-substituent was replaced by a benzoate group in a subsequent step, using the initial product as a handle for further modification. And a sophisticated example shows the reactant prepared with high anti-selectivity through an auxiliary-directed aldol reaction, and the chiral auxiliary then participated in the iodocyclization and was cleaved in the process, streamlining the synthesis and controlling chirality. Finally, there's a simple example of cyclization effectively carried out using NBS.
Okay, what about sulfonyl cyclization and selenyl cyclization? Similar idea, but with sulfur or selenium electrophiles.
It's exactly. Similar to halocyclization, reactants with internal nucleophiles are also susceptible to cyclization initiated by electrophilic sulfur reagents. This reaction class is known as sulfonyl cyclization. As with iodolactonization, unsaturated carboxylic acids typically yield products that result from anti-addition, forming thiolactones. Alcohols, similarly, undergo cyclization to form cyclic ethers containing sulfur.
And selenyl cyclization is the selenium version.
Precisely. The corresponding reactions using selenium electrophiles are called selenyl cyclization. Carboxylate groups can undergo selenyl ionization. Hydroxy groups can undergo selenyl aldehydification, and nitrogen-containing groups like amides or amides can undergo selenyl amidation, provided they are appropriately positioned for intramolecular capture of the selenoranium ion intermediate.
Do the same principles of stereochemistry and ring size apply?
Yes. The internal nucleophilic capture of a selenoranium ion, intermediate the selenium bridge species, is governed by general principles similar to those of other electrophilic cyclizations. The stereochemistry of cyclization can usually be predicted based on a cyclic transition state that favors a pseudo-equatorial orientation of the substituents, minimizing steric hindrance as the ring closes. While exocyclization is generally preferred, based on Baldwin's rules and sterics, there isn't a strong prohibition against endocyclization. Interestingly, in certain cases, aryl-controlled regioselectivity, where a phenyl group directs the reaction, can actually override the typical exo preference, leading selectively to an endocyclized product.
Which selenium reagents are used for this?
Various electrophilic selenium reagents, like those we discussed earlier, can be employed for selenyl cyclization. N-phenylselenin phthalimide, PSL or NSP, is highlighted as an excellent reagent for this process, particularly for forming large ring lactones. Its advantage in this specific application stems from the low nucleophilicity of phthalimide, the leaving group, which does not compete with the remote internal nucleophile that is trying to form the large, often strained ring. It keeps side reactions to a minimum. The reaction of phenylselenyl chloride, or N-phenylselenyl phthalimide with unsaturated alcohols, leads reliably to the formation of N-phenylselenyl ethers. Phenylselenyl triflate is another useful reagent capable of cyclizing unsaturated acids and alcohols. Phenylselenyl sulfate can even be prepared in situ by oxidizing diphenyl diselenate with ammonium peroxide disulfate.
Can we see some examples of these sulfur and selenium cyclizations?
Certainly. For sulfonyl cyclizations, we see examples like a 6-exosulfonothermification reaction initiated by phenylsulfonyl chloride. Another cyclization is mediated by dimethylthiosulfonium tetrafluoride, showcasing a different sulfur electrophile. There are other compelling examples of 5-exyl cyclizations using various sulfonylating agents, and examples using sulfonamides as the electrophiles. We also see the cyclization of a carbonate, where the carbonyl oxygen serves as the internal nucleophile, and an example of a 5-endo aminocyclization where a nitrogen atom participates in the ring closure.
And for selenyl cyclizations?
Numerous examples showcase selenyl aldehydifications. where an alcohol group cyclizes onto an alkene activated by a selenium electrophile. Importantly, all of these examples consistently exhibit anti-stereochemistry, reflecting that bridged intermediate. We also see examples of selenylactonizations, where a carboxylic group acts as the internal nucleophile, and cases involving amido groups acting as the internal nucleophile. In one example, it's a 5-exocyclization, where the amido oxygen is the more reactive nucleophilic site, leading to an iminolactone product. But in contrast, another example shows how geometric factors can specifically favor N-cyclization over O-cyclization for the amide group.
You mentioned chiral versions of these earlier.
Yes, and this is truly exciting. What's been developed are chiral selenylating reagents. For example, reagent 4 in the text, which is a complex chiral bisoxylene selenium reagent, has been shown to be capable of affecting highly enantioselective additions and cyclizations. It achieves more than 90% enantioselectivity in typical reactions. This opens up crucial pathways to synthesizing highly pure single enantiomer molecules, a major goal in modern synthesis, especially for pharmaceuticals.
Okay, let's move on to cyclization induced by the mercuric ion. Similar idea again.
Similar concept, yes. Electrophilic attack by the mercuric ion, Ag2+, can also effectively induce cyclization by the intramolecular capture of a nearby nucleophilic functional group. A variety of both oxygen and nitrogen nucleophiles can participate in these cyclization reactions. This versatility has led to numerous synthetic applications for building cyclic structures using mercury.
What do we know about the mechanism and preferences here?
Mechanistic studies have been performed on several alkanol systems. For example, the ring size preference for the cyclization of 4-hexanol depends significantly on the specific mercury reagent used. The more reactive mercuric salts, like mercuric trifluoroethane sulfonate or mercuric nitrate, actually favor 6-endo addition. It is proposed that this preference is due to the reversal of formation of the kinetic exoproduct. This means the initial, fastest formed product might be the 5-exo ring. But under the conditions with these reactive salts, it can reopen and reclose to form the more thermodynamically stable 6-endo product.
So it equilibrates.
It seems so. And what's intriguing is that this equilibration doesn't seem to be solely dependent on acid catalysis, as the thermodynamically favored product is still formed even in the presence of acid scavenging agents like tetramethylurea, TMU. The exact mechanism of equilibration might be more complex.
Can electronics override the normal exo preference?
Yes. In 5-aryl-4-hexanols with electron-releasing groups, ERGs, on the aryl ring, electronic factors can actually outweigh the inherent exo preference. This occurs because the ERG substituents increase the positive character at the C5 position, guiding the regioselectivity towards the endo pathway. The cyclization of guanonyl alkenes, with a hydroxyl group 4 carbons away from the double bond, is controlled by a fascinating conformation-dependent strain in the exotransition state. Specifically, the C5-C6 bond undergoes rotation to minimize A13 strain, a type of steric interaction. Contrastingly, in the corresponding E-alkene, where this specific steric factor is not present, the cyclization is much less stereoselective. A stabilizing interaction between a nearby siloxy-oxygen and the Hg2+ center has also been suggested as a factor influencing selectivity, so multiple subtle forces are at play.
Are there limits to the ring sizes you can make?
It appears so. The use of highly reactive mercury reagents with a series of dibenzyl carbonyls showed exclusive exocyclization for the formation of 5, 6, and 7-membered rings, but not for 8-membered rings. This highlights clear limits on ring size formation for this method. 8-membered rings seem difficult.
Can you make nitrogen rings this way?
Yes, benzyl carbonates have proven useful for forming both 5- and 6-membered nitrogen-containing rings through mercuric ion-induced cyclization. The observed selectivity for nitrogen nucleophilicity over oxygen nucleophilicity in these carbamates is a result of nitrogen being able to form a more favored ring size, 5 or 6-membered, compared to the carbonyl oxygen of the carbamate, which would typically lead to a less favorable 7- or 8-membered ring. Geometry dictates the outcome.
And you mentioned using that radical demercuration trick here, too.
Absolutely. Recall our earlier discussion about the free, radical nature of sodium borohydride demercuration. What's fascinating is that the trapping of the radical intermediate by oxygen can be cleverly exploited as a method for the direct introduction of a hydroxy substituent instead of a hydrogen atom during the reduction step. This provides a strategic way to achieve selective functionalization right at the site of cyclization.
Let's look at some examples of these mercury cyclizations.
Okay. Several entries involve acyclic reactants that successfully cyclize to yield XO5 products, demonstrating the kinetic preference for this ring closure mode. In some cases, the mercury is subsequently removed reductively. What's interesting is that in one example, the inclusion of triethylboron during the reduction step was found to significantly improve the yields. Little tricks like that often make a big difference. Another provides an example of a successful XO6 cyclization.
And the hydroxy introduction.
Yes, crucially, in two of these examples, a hydroxy group is specifically introduced at the cyclized carbon during the demercuration step by performing the reduction in the presence of oxygen, using that radical trapping method. One cyclization reaction shown was a key step used in the synthesis of lionine, which is an aggregation pheromone of the ambrosia beetle, illustrating real-world applications in natural product synthesis. Another shows a fascinating transannular 5-exo cyclization, where a ring forms across a larger existing ring complex architecture. And there's an example of lactone formation through intramolecular carboxylic capture. In this specific case, the product was isolated, still containing the mercury as a mercuryl chloride, showing that sometimes the demercuration isn't done immediately.
Has there been progress on making these mercury cyclizations enantioselective?
Yes, some significant progress has been made, which is very exciting. Several bioxazolinane (BOX) ligands have been investigated as chiral auxiliaries, complex to the mercury regent. For example, the diphenyl BOX ligand, when used in conjunction with mercuric trifluoroacetate, can lead to the formation of tetrahydrofuran rings with impressive enantiomeric excesses like 80% E. Other biazoxazoline ligands derived from tartaric acid have been screened, with the best results sometimes over 90% in several cases obtained with a 2-naphthol ligand, labeled as NaphBOX in the text. This represents a major advancement in controlling the absolute stereochemistry of these reactions using chiral catalysts.
Okay, let's shift focus now to additions involving alkenes and alkynes. These have different bonding, so they react differently.
Yes, both alkenes, which have two adjacent carbon-carbon double bonds, and alkynes with carbon-carbon triple bonds, require special consideration when it comes to the mechanisms of electrophilic addition. Their unique geometries and bonding arrangements lead to distinct reactivity patterns compared to simple alkenes.
What's the issue with alenimans?
The protonation of the simplest alene, CH2, CCH2, presents an interesting mechanistic puzzle. One might immediately presume that protonation would lead to the more stable allyl cation, CH2, CH2+, which is nicely resonance stabilized. However, there's a crucial stereoelectronic facet related to orbital overlap to the reaction that defies this simple assumption.
Why doesn't it form the allyl cation?
Okay, think about the geometry. If protonation were to occur at the center carbon of alene without a concomitant rotation of one of the terminal methylene groups, it would lead to a primary carbocation where the adjacent pi bond would be orthogonal at a 90-degree angle to the MTP orbital of the carbocation. This orthogonal arrangement prevents effective resonance stabilization by the pi system. The orbitals just can't overlap correctly. As a direct result of this unfavorable stereoelectronic arrangement, protonation of alene both in solution and in the gas phase actually occurs at a terminal carbon.
Ah, so it avoids that bad orbital alignment.
Exactly. This terminal protonation gives rise to the 2-propanol cation, CH3C plus equals CH2, which is a vinyl cation, not the allyl cation. This is a surprising fact that highlights the critical importance of orbital alignment in reaction mechanisms. Geometry dictates reactivity.
So what products do you get when you add HX to alene?
The addition of HCl, HBr, and HI to alene has been studied in detail. In each case, a 2-halopropane is formed, for example, CH3CX, which directly corresponds to that protonation at a terminal carbon. What's interesting is that the initial 2-halopropane product, being an alkene itself, can then undergo a second addition reaction with more HX, leading to the formation of 2-DL2 dihalopropanes, example, CH3CX2CH3. The regiochemistry observed in the second step reflects the electron donating effect of the initial halogen substituent. We should also briefly note that dimers can sometimes be formed as side products.
Do substituents on the alene change this?
Yes, they can. The presence of a phenyl group on the alene changes the game. It results in the formation of products that derive from protonation at the center carbon. Similarly, if there are two alkyl substituents, as in olefin-dimethylene, this also steers protonation towards the center carbon.
Why the shift?
These substituent effects are due to the enhanced stabilization of the carbocations that result from protonation at the center carbon in these cases. Even if full allylic conjugation isn't the primary stabilizing factor, due to that initial geometry problem, the aryl and alkyl substituents make the resulting vinyl cation, where the positive charge is on a double-bonded carbon, more stable than the alternative, which would be a secondary vinyl cation formed from terminal protonation in these substituted systems. So the substituents tip the balance of stability.
Okay, let's move to alkynes then. How do they react with acids?
Acid-catalyzed additions to terminal alkynes, HGCr, consistently follow the Markovnikov rule. This means the hydrogen adds to the carbon with more hydrogens, the terminal carbon, and the electrophilic part of the reagent, or the resulting positive charge in the intermediate vinyl location, ends up on the more substituted internal carbon. For example, adding HBr to one octine gives 2-bromo-1-octane.
Are these reactions fast?
They can be quite slow. However, their rate and selectivity can be considerably enhanced by using an added quaternary bromide salt, like P4N plus Br, in a specific solvent mixture, like 1.1 TF8CH2Cl2. Even under these favorable conditions, the reactions are still often quite slow, hundreds of hours sometimes. But they provide clean formation of the anti-addition product in high yields. Similar to alkenes, surface-mediated addition of HCl or HBr to alkynes can also be achieved in the presence of silica or alumina, offering a practical way to speed things up using reagents generated in situ.
Is there kinetic versus thermodynamic control here too?
Yes, for reactions like HCl addition to 1-phenylpropene, the initial kinetic products result from syn addition. However, upon continued exposure to the acidic conditions, these kinetic products will isomerize to the thermodynamically more stable Z-isomer, highlighting a dynamic equilibrium that can shift product distribution over time. Again, what you isolate depends on when you stop the reaction.
Are the initial addition products to alkynes always stable?
That's an important point. No, they are not always stable. For example, the addition of acetic acid, CH3CO2H, to an alkyne initially forms an enol acetate. These enol acetates are vinyl esters, and they are often rapidly converted, hydrolyzed or isomerized, to the corresponding ketone under the acidic reaction conditions. So you might aim for the enol acetate, but end up with the ketone instead.
So how do you make ketones from alkynes reliably?
The most synthetically valuable method for converting alkynes directly to ketones is through mercuric ion, He2+, catalyzed hydration. This is analogous to the oxymercuration of alkenes but leads to ketones. Terminal alkynes consistently yield methyl ketones, RCOCH3, in accordance with Markovnikov's rule. The oxygen ends up on the internal carbon. Internal alkynes, however, typically give mixtures of ketones unless there's a specific structural feature, like conjugation or a very different substitution pattern, that promotes regioselectivity.
What's the mechanism? Still a mercurium ion?
Yes. Reactions using mercuric acetate in other nucleophilic solvents, like acetic acid or methanol, proceed through acetoxy or methoxyalkenyl mercury intermediates. These intermediates can then be reduced or more commonly solvolized, reacted with solvent water, to form the ketones, often via an intermediate enol which tautomerizes. The observed regiochemistry strongly indicates a mercurium ion, intermediate, perhaps more skewed than with alkanes, that is opened by nucleophilic attack at the more positive carbon, meaning the additions consistently follow Markovnikov's rule. Examples show various alkenes converting to their respective ketones, often with high yields, showcasing the practicality of this method.
What about halogen addition to alkenes, like chlorination?
The addition of chlorine, Cl2, to 1-butene is slow in the absence of light. When the addition is initiated by light, and if butene is present in large excess, to minimize addition of a second Cl2 molecule, the major product is E-2-dichlorobutene, suggesting an anti-addition process under these conditions. In acetic acid, both 1-pentyne and 1-hexene primarily give the syn addition product. For internal alkynes like 2-butene and 3-hexene, the major products are chlorovinyl acetates of E configuration, meaning solvent incorporation is common. Some dichloral compounds are also formed, with more of the E anti-addition than the Z syn addition isomer observed. It's complex.
How do we interpret that mix of outcomes?
The reactions of internal alkynes are believed to proceed through a cyclic chloronium ion intermediate, similar to alkenes, leading predominantly to anti-addition products or solvent incorporation. However, terminal alkynes seem to react via rapid collapse of a vinyl cation, suggesting a less stable or shorter-lived intermediate compared to the internal alkyne halonium ions, which might explain the tendency towards syn addition sometimes observed.
Do selenium reagents react with alkenes?
Yes. Alkynes are also reactive toward electrophilic selenium reagents, such as phenylselenyl tosylate. The reaction occurs with striking anti-stereoselectivity, again suggesting a bridged intermediate. Aryl-substituted alkynes show good regioselectivity, but interestingly, alkyl-substituted alkynes do not. This difference in regiochemical control depending on substituents is a key detail.
And you mentioned organometallics are important here.
Yes, what's fascinating is that some of the most synthetically useful addition reactions of alkynes are those involving organometallic reagents. These reactions are particularly important because they can lead to the formation of new carbon-carbon bonds, a cornerstone of molecular construction. We will delve into these powerful reactions in much greater detail in Chapter 8. Consider this a trailer.
Okay, now for a major topic. Addition via organoborane intermediates, starting with hydroboration. This sounds important.
Oh, it's incredibly important. Let's unpack this. Borane, BH3, is a unique and highly useful reagent. With only 6 valence electrons on boron, it is a very avid electron pair acceptor, making it a strong Lewis acid. Pure borane actually exists as a dimer, diborane, B2H6, where 2 hydrogens bridge the borons. However, antiprotic solvents that can act as electron pair donors, think ethers like THF or tertiary amines or sulfides, borane readily forms stable Lewis acid-base adducts. The most common one used is BH3.THF, borane complexed with tetrahydrofuran.
And this reacts with alkenes?
Yes, borane dissolved in solvents like THF or dimethyl sulfide undergoes rapid addition reactions with most alkenes. This reaction, known as hydroboration, the net addition of an HB bond across a double bond, has been extensively studied, most notably through the pioneering work of H.G. Brown and his associates, which earned him a Nobel Prize. This work has led to the development of a wide variety of incredibly useful synthetic processes that really changed organic synthesis.
What are the key characteristics? You mentioned regioselectivity and stereospecificity.
Exactly. Hydroboration is renowned for being both highly regioselective and stereospecific. Let's break that down. First, regioselectivity. Here's where it gets really interesting and synthetically powerful. The boron atom preferentially bonds to the less substituted carbon atom of the alkene.
Wait, less substituted. That's the opposite of Markovnikov's rule.
Precisely. This is often referred to as anti-Markovnikov addition, as it's opposite to what we saw with hydrogen halide additions. This preference is a powerful combination of steric and electronic effects. Electronically, borane acts as an electrophilic reagent. While it is electrophilic, studies with substituted styrenes show only a weakly negative Warval value, Nennis of 0.5, indicating a relatively small electronic driving force compared to something like bromination plus equals 4.3. However, this small effect still favors the addition of the electrophilic boron atom at the less substituted end of the double bond. Crucially, in contrast to the addition of protic acids, HX, to alkenes, it is the boron, not the hydrogen, that is the more electrophilic atom in borane.
And sterics reinforce this.
Strongly reinforced by steric factors. Hydroboration is typically performed under conditions where the borane eventually reacts with 3 alkene molecules to form a trialkylborane, or 3B. The addition of the second and third bulky alkyl groups would create significant steric repulsion if the boron were trying to attach to the more crowded internal, more substituted carbon. Therefore, the less hindered carbon is strongly preferred for boron attachment just to avoid bumping into things. You can visualize the non-bonded repulsions increasing dramatically at the more substituted position.
Are there ways to make it even more selective?
Yes. Chemists have cleverly developed specialized alkylboranes that enhance this selectivity. Table 4.3 in the text provides compelling data. Mono and dialkylboranes like 9-BBN, 9-borb-cyclo-3.3.1 non-nan, the functionalized and diacylborane, dissect isomilborane, exhibit even higher regioselectivity than diborane itself. These bulky, specialized derivatives are widely used in synthesis because they ensure exceptionally clean regiochemical outcomes. They are much pickier about where they add. And these reagents are prepared simply by controlling the stoichiometry of hydroboration of specific sterically hindered alkenes like 2-tetranyl-3-dimethyl-2-butene for diacylborane or 1-gonfulphycylcatadiene for 9-BBN.
Okay, that's regioselectivity. What about stereospecificity?
Hydroboration is a stereospecific syn addition. This means that the boron and the hydrogen atoms add to the same face of the carbon-carbon double bond. This occurs through a concerted 4-center transition state, where bonding to both boron and hydrogen happens essentially simultaneously as the BH bond adds across the CT bond.
Can you explain that transition state a bit more?
Sure. In molecular orbital terms, the addition is viewed as taking place by an interaction between the filled alkene orbital, the electron source, and the empty p orbital on the boron atom, the electron sink. This is accompanied by a concerted, simultaneous formation of the carbon-hydrogen bond from the BH bond. This highly ordered cyclic transition state enforces the syn addition geometry.
Does it prefer one face of the alkene over the other?
Yes, as with most reagents, there is a preference for the borane to approach from the less hindered face of the alkene. However, because diborane itself, or BH3 and THF, is a relatively small molecule, its facial stereoselectivity isn't always very high for unhindered alkenes. Table 4.4 in the text presents data comparing the direction of approach for 3 cyclic alkenes. The products in all cases still result from syn addition, but mixtures can arise both from potentially low regioselectivity and from addition occurring to both faces of the double bond. Even 7,7-dimethylnorborne, which is quite sterically hindered on one face, shows only a modest preference for endo-addition from the less hindered face with diborane. Crucially, this facial selectivity is significantly enhanced when the bulkier reagent 9-BBN is used, demonstrating again the power of steric control with these modified boranes.
Are there other types of boranes used? Haloboranes.
Yes, haloboranes, such as BH2Cl, BH2Br, BHCl2, and BHBr2 are also valuable hydroborating reagents. What's interesting is that these compounds are somewhat more regioselective than borane itself, perhaps due to electronic effects of the halogen, though they otherwise show similar reactivity patterns, still syn addition, anti-Markovnikov. A useful aspect of the chemistry of haloboranes is the potential for sequential introduction of different substituents at the boron atom. The halogens can be replaced by alkoxide groups, or, importantly, by hydride, using reducing agents. When a halogen is replaced by hydride, it regenerates a BH bond, allowing for a second, different hydroboration step, enabling more complex synthetic strategies like making mixed alkylboranes, for example, RBX2 plus LiOH4 LaBH2, then react with a different alkene.
What about anemer borane complexes?
While most simple amine-borane complexes aren't highly reactive towards hydroboration, the pyridine complex of borane, BH3, can be activated by reaction with iodine. The active reagent is thought to be the pyridine complex of iodoborane, BH2Y. The resulting alkyl-boranes can then be subjected to standard oxidation to form alcohols, or isolated as stable potassium trifluoroborates, which are useful shelf-stable intermediates.
And boranes with oxygen substituents like catechol-borane.
Right. Catechol-borane and penachol-borane are hydroborating reagents, where the boron atom has two oxygen substituents attached through a cyclic structure. These are significantly less reactive than alkyl or haloboranes. This reduced reactivity is because the boron's electron deficiency is partially attenuated or lessened by the argon-donating effect of the oxygen atoms feeding electron density into the empty boron orbital. Despite their lower reactivity, they are useful reagents for certain applications. For example, the reactivity of catechol-borane has been found to be substantially enhanced by adding 10–20% of N-dimethylacetamide, DMA, to dichloromethane as a co-solvent. A little additive can make a big difference.
But where do these oxygenated boranes really shine?
Here's where they become incredibly important. Catechol-borane and penachol-borane are especially useful in hydroborations that are catalyzed by transition metals. Wilkinson's catalyst, RHPPH3Cl, a rhodium complex, is among those frequently used, but many others exist.
So the metal helps the less reactive borane add. How?
The general mechanism for this transition metal catalysis is believed to be similar to that for homogeneous hydrogenation, which uses similar catalysts. It likely involves an oxidative addition of the BH bond of the borane to the metal center. This generates a metal hydride intermediate, MH, with the boron attached, MB. The alkene then coordinates to the metal, and then the H and B groups transfer sequentially from the metal to the alkene, usually resulting in overall syn addition.
Does the catalyst affect selectivity?
Profoundly. Variations in the catalyst, the specific metal like rhodium or iridium, and the ligands, the molecules bound to the metal, often phosphorus-containing ligands, can lead to dramatic changes in both regio and enantioselectivity. For example, the hydroboration of vinylerenes, like styrene and related compounds, can be specifically directed to the internal secondary borane, Markovnikov-like regiochemistry, by using a specific rhodium catalyst, RHCOD2BF4. This is the opposite of uncatalyzed hydroboration. What's more, these reactions can be highly enantioselective when a chiral phosphorus ligand, like josephos, is incorporated, allowing for the synthesis of specific enantiomers of these secondary boranes. Conversely, certain iridium catalysts can give very high selectivity for formation of the primary borane, anti-Markovnikov, demonstrating incredible control just by changing the metal. Other catalysts, like dimethyldecanosine, have also been described. The possibilities are vast.
Does the catalysis help with functionalized alkenes too?
Yes, catalyzed hydroboration has proven valuable in controlling the stereoselectivity of hydroboration of functionalized alkenes. For example, allylic alcohols and ethers generally yield mainly syn products relative to the oxygen group when the hydroboration is catalyzed by RHPPH3–3Cl. This is opposite to direct hydroboration with bulky reagents like 9-BBN, which often gives mainly the antiproduct for these substrates due to steric repulsion from the oxygen group.
Why the difference in stereochemistry with the catalyst?
The stereoselectivity of the catalyzed reaction appears to be directly associated with the complexation step, where the alkene and borane bind to the metal, which is actually product determining. The preferred orientation of approach of the alkene to the metal complex is anti to the oxygen substituent of the allylic alcohol, which acts as an electron acceptor in this context. More electronegative groups on the oxygen enhance reactivity. The preferred conformation of the alkene during this complexation places the smaller hydrogen oriented toward the double bond, which ultimately leads to a syn relationship between the alkyl chain and the oxygen substituent in the final product after BH addition. It's about how the molecule docks onto the catalyst.
And chiral ligands give enantioselectivity here too.
Absolutely. The use of chiral ligands in these transition metal catalysts can lead to highly enantioselective hydroboration. Rhodium complexes with chiral ligands like BINAP, structure C in the text, and the related structure D have shown good to excellent stereoselectivity in the hydroboration of styrene and related compounds, producing products with high enantiomeric excess, EE. This is a major route to chiral building blocks.
Now, what about this boron migration? You mentioned hydroboration is reversible.
Yes, here's another fascinating aspect. Hydroboration is thermally reversible. Borane hydrogen, BH moieties, can be eliminated from alkyl branes at elevated temperatures, typically 160 degrees C and above. The reaction runs backward temporarily. However, at equilibrium, the addition products, the alkyl branes, are still strongly favored thermodynamically. But this reversibility provides a powerful mechanism for the migration of the boron group along the carbon chain. This occurs through a series of reversible eliminations, alkene plus HB, and readditions. The boron effectively hops along the chain.
Where does it end up?
It migrates away from internal positions towards the end of the chain. At equilibrium, the major trialkylborane isomer formed is the least substituted terminal isomer that is accessible. This is because this isomer minimizes unfavorable steric interactions. The boron wants to be at the least crowded spot. For example, an internal branched alkylborane will isomerize upon heating to put the boron at the very end of the longest straight chain portion.
Are there limits to this migration?
Yes, a key limitation is that migration cannot occur past a quaternary carbon, a carbon bonded to 4 other carbons, because the required elimination of the BH unit, which needs a hydrogen on the adjacent carbon, is sterically blocked. It hits a dead end. Interestingly, these migrations are more facile, meaning they occur more easily for highly substituted, like tetrasubstituted alkanes, and can happen at milder temperatures, maybe 50-60 degrees C. Furthermore, bulky substituents already on the boron atom can also facilitate the migration process. For example, bicyclo 2.2.2 octanol boranes were found to be particularly useful reagents for promoting these migrations because the bicyclic groups don't rearrange themselves.
Does it happen within one molecule?
Evidence suggests that boron migration occurs intramolecularly, within the same molecule, rather than the boron detaching completely and reattaching elsewhere. Computational studies have actually located a plausible transition state involving an electron-deficient complex between the boron and the transient alkene, which is about 20-25 kilocalmol higher in energy than the trialkylborane. This TS describes the migration and provides a theoretical basis for this intriguing phenomenon.
Can catalysts help here too?
Yes. What's truly exciting is that migration of boron to terminal positions can be observed under much milder conditions when transition metal catalysts are present. For example, hydroboration of 2-methyl-3-hexene by pinacolborane in the presence of Wilkinson's catalyst, or PPH33Cl, leads directly to the formation of the terminal boronate ester. The catalyst facilitates both the initial addition and the subsequent migration to the end of the chain, all in one pot.
Okay, so we've made these organobranes. What can we do with them? You mentioned they are useful intermediates.
Extremely useful intermediates. The organoboranes formed through hydroboration have proven to be very useful intermediates in organic synthesis because the carbon-boron bond can be readily transformed into various other functional groups with high predictability and stereochemical control. We will specifically discuss methods where the boron atom can be replaced by hydroxy-OH, carbonyl CO, amino NH2, or halogen groups like BRY. Just a note, carbon bond-forming reactions of organoboranes are incredibly important too, but they covered in Chapter 9, so we won't dwell on them here.
What's the most common transformation?
By far the most widely used reaction of organoboranes is their oxidation to alcohols. Alkaline hydrogen peroxide, H2O2 in basic solution, typically NaOH, is the reagent almost universally employed to effect this oxidation. It's a very reliable reaction.
How does that work? How does the boron get replaced by oxygen?
It's a really elegant mechanism. It involves a series of sequential alkyl group migrations from boron to oxygen. First, the hydroperoxide anion, HOO, formed from H2O2 under basic conditions, acts as a nucleophile, attacking the electron-deficient boron atom. Then, in the key step, one of the alkyl groups attached to boron migrates from boron to the adjacent oxygen atom, simultaneously expelling a hydroxide ion as a leaving group. This process repeats 2 more times for a trialkylborane, resulting eventually in a trialkylbore ester, RO3b, where all 3 alkyl groups are now attached to oxygen via boron. Finally, these ROB bonds of the bore ester are readily hydrolyzed, cleaved by water, in the alkaline aqueous solution, generating 3 equivalents of the desired alcohol, ROH, and boric acid, BOH3.
And the stereochemistry of this replacement.
This is crucial for synthetic planning. The replacement of the carbon-boron Cb bond by a carbon-oxygen CO bond occurs with perfect retention of configuration at the carbon center. This means if you start with a specific stereoisomer of an alkene and hydroborate it, which is syn addition, the stereochemistry at the carbon where the boron was attached will be perfectly preserved as the oxygen functional group is introduced.
So hydroboration oxidation gives overall syn addition of H and OH.
Exactly. Syn addition of H and B, followed by replacement of B with OH with retention. So the net result is syn addition of H and OH. And remember, the regiochemistry, in combination with the stereospecific syn hydroboration and its anti-Markovnikov regioselectivity, boron on the less substituted carbon. This oxidation allows for the highly predictable synthesis of alcohols with a regiochemistry that is complementary to that observed by direct hydration or oxymercuration. In simpler terms, hydroboration oxidation allows you to place the HOH group on the less substituted carbon of the original alkene, whereas direct acid hydration or oxymercuration puts the HOH on the more substituted carbon. This gives chemists a choice and is incredibly powerful for synthetic control.
Are there other ways to oxidize the boranes besides peroxide?
While alkaline hydrogen peroxide is standard, other oxidants can also affect the borane to alcohol conversion. These include oxone, which is a potassium peroxymonosulfate complex, often recommended for oxidations performed on a large scale. Molecular oxygen O2 itself can work, particularly effective in specialized perfluoroalkane solvents. Sodium peroxycarbonate is another option, and implanine oxides like trimethylamine N oxide, PMAO, can also be used.
Can you oxidize them further, say to ketones or aldehydes?
Yes, more vigorous oxidants such as chromium reagents like potassium dichromate Ke2Cr2O7 or chromic acid Cr3 in acid can affect not just replacement of boron, but also further oxidation of the intermediate alcohol to the carbonyl level, ketones or aldehydes. For example, a borane derived from an internal alkane, leading to a secondary alkylborane, can be oxidized directly to a ketone using chromic acid. An alternative, more modern and often milder procedure for oxidation directly to ketones involves treating the alkylborane with a quaternary ammonium perwithnate salt, like TPAP, and an amine oxide, like NMO, as a co-oxidant. This method is shown in Scheme 4.9, Entry 6, and is highly effective. There's also a powerful method for synthesizing carboxylic acids directly from terminal alkenes. It involves hydroboration using dibromoborane dimethylsulfide, followed by hydrolysis and then CRAVI oxidation. This sequence effectively converts a terminal alkene, RCHCH2, into a carboxylic acid with 1 extra carbon, RCH2CO2H.
What about replacing boron with nitrogen to make amines?
Yes, that's another very useful transformation. The boron atom can be replaced by an amino group, NH2. The key reagents for this transformation are chloramine, NH2Cl, or more commonly, hydroxylamine osulfonic acid, NH2OS3H. The mechanism of these amination reactions is remarkably similar to the hydrogen peroxide oxidation we just discussed. The nitrogen-containing reagent initially acts as a nucleophile, adding to the electron-deficient boron. A subsequent beta-N rearrangement then occurs, where an alkyl group migrates from boron to nitrogen with simultaneous expulsion of a chloride or sulfate ion. Typically, only 2 of the 3 alkyl groups migrate efficiently from a standard trialkylborane in this reaction. And importantly, just like in the oxidation, this migration step occurs with retention of configuration at the migrating carbon. The desired primary amine is then released by hydrolysis of the boron-nitrogen intermediate.
Can you make it more efficient?
Yes. The alkene starting material can be used more efficiently, getting more amine per alkene, if the hydroboration is initially performed with dimethylborane, E2BH, leading to an RCH2ACH2B CH32 intermediate. Here, the desired alkyl group is more likely to migrate preferentially over the methyl groups. You can also synthesize secondary amines, RNHR, by reacting trisubstituted boranes with alkyl or arylizides, RN3. The most efficient borane intermediates for this are monoacyldichlorophoranes, RCHS2CH2BCl2, which are conveniently generated by the reaction of an alkene with BHCl2.E2O. The sequence involves hydroboration, reaction with the azide, where a BN rearrangement occurs, followed by hydrolysis to yield the secondary amine. This reaction has even been applied to prepare IN-methylamino acids, Secondary amines can also be prepared using the N-chloro derivatives of primary amines reacting with trialkylburanes.
And finally, replacement by halogen.
Yes, organoborane intermediates provide a complementary route to synthesize alcoholides, again with that useful anti-Markovnikov regiochemistry. Replacement of boron by iodine is rapid and high-yielding in the presence of base, for example, sodium methoxide and methanol. If less basic conditions are preferred, the use of iodine monochloride, ICl, and sodium acetate also gives good yields of alkyl iodides. Bromination is similar using Br2 in base, and as with hydroboration oxidation, the regioselectivity of hydroboration halogenation is opposite to that observed by direct ionic addition of hydrogen halides to alkanes. This means that terminal alkanes, which would normally give secondary halides with HX, yield primary halides via hydroboration halogenation. This offers powerful synthetic control over halide placement. For example, RCHCH2 with B2H6 followed by B2NaOH yields RCH2CH2Br.
Let's look at scheme 4.9 again, which summarizes these transformations beautifully.
Okay, section A shows alcohol formation, entries 1-1. These clearly demonstrate the remarkable regioselectivity and stereospecificity of hydroboration oxidation. Entry 1 shows the formation of trans-2-methylcyclohexanol, illustrating both the anti-Markovnikov regioselectivity, boron adds to the less substituted C1, and the syn addition, H and B add to the same face, followed by retention of configuration during oxidation, OH replaces B where it was. Entry 2 highlights the facial selectivity of hydroboration, where the borane adds anti from the bottom face to a pre-existing endomethyl group pointing down. Entry 3 illustrates all aspects, regio, stereo, and facial selectivity with syn addition occurring anti from the less hindered face to a dimethyl bridge in a pine structure. Very precise. Entry 4 stereoselectivity is a result of the preferred conformation of the alkene and the strategic approach sent to the smaller methyl group, rather than a bulkier 2-furol group.
Section B covers ketones and aldehydes.
Right, entries 5-7. These showcase the oxidation of boranes to the carbonyl level. Entry 5 uses classic chromic acid to directly obtain a ketone from an alkyl borane derived from an internal alkene. Entry 6 employs that milder ruthenium catalyst, TPAPI, with NMO as co-oxidant, directly converting the borane to a ketone. This reagent combination is also capable of yielding aldehydes from boranes derived from terminal alkenes. Entry 7 shows that pyridinium chlorochromate, PCC, another common oxidant, can also be used to obtain aldehydes from terminally hydroborated alkenes.
Section C for amines.
Yes, entries 8-9. These entries illustrate effective methods for the amination of alkenes via organoborane intermediates, forming primary amines with retention of configuration.
And D for halides.
Correct, entries 10-11. These entries demonstrate the preparation of alkyl halides, bromide and iodide, from organoboranes, highlighting the complementary anti-Markovnikov regioselectivity compared to direct HX addition.
Now let's get into NHO-selective hydroboration. This sounds like a major advance.
It truly is a powerful application. Several alkyl boranes are now available in enantiomerically enriched or pure form. This means they exist predominantly as one of their mirror image forms, chirality. These pure chiral boranes can then be used to hydroborate procryl alkanes, alkanes that can form two enantiomeric products, and subsequently prepare enantiomerically enriched alcohols and other compounds accessible via organoborane intermediates. This is absolutely crucial for synthesizing pharmaceutical drugs, which often require a specific enantiomer for biological activity and safety.
Where do these chiral boranes come from?
One primary route is through the hydroboration of readily available terpenes. Terpenes are natural products, often from pine trees or citrus fruits, that frequently occur naturally in enantiomerically enriched or pure forms. They provide a fantastic renewable source of chirality from nature's chiral pool. The most thoroughly investigated and synthetically powerful of these is bis-isopenocamphyl borane, derived from ipane, and often abbreviated as IPC2BH. It can be prepared in essentially 100% enantiomeric purity directly from the readily available terpene opane. What's more, both enantiomers of ipene are available, meaning chemists can prepare both enantiomers of IPC2BH, giving complete control over the absolute stereochemistry of the final products. Other examples of chiral organoboranes mentioned are derived from different terpenes like longophyllene, 2-carene, and limone, highlighting the diversity of chiral sources available.
How does IPC2BH achieve this enantioselectivity? What's the mechanism?
It comes down to the specific rigid 3D shape of the reagent. IPC2BH adopts a specific preferred conformation that effectively minimizes steric interactions within the reagent itself. This conformation can be schematically represented, as in structures H and I in the text, where different groups, small, medium, large, on the chiral terpene backbone, provide a well-defined chiral steric environment right around the reacting boron atom. The steric environment of the boron atom in this specific conformation is such that Z-alkanes, where larger groups are on the same side, encounter significantly less steric encumbrance, less crowding, when they approach in one specific orientation, leading to transition state I, compared to the alternative orientation, transition state H. This subtle but significant steric differentiation in the transition state energy is what leads to the high enantioselectivity. The alkene prefers to dock in the less crowded orientation.
Does it work equally well for all types of alkenes?
No, the degree of enantioselectivity achieved with IPC2BH is not uniform across all simple alkenes. It's quite sensitive to the alkene structure. Z-disubstituted alkenes generally yield good enantioselectivity, typically in the range of 75–90% enantiomeric excess, EE. However, E-alkenes, where larger groups are on opposite sides, and simple cycloalkenes typically give much lower enantioselectivity, often only 5–30% EE. The steric differentiation isn't as effective for these structures. What's interesting and perhaps a bit surprising is that vinyl ethers exhibit good enantioselectivity for both their E and Z isomers. This just demonstrates the nuanced interplay of steric and electronic factors in controlling these reactions.
What about using just one isopenocamphyl group, monoisocampylborane?
Yes, monoisocampylborane, IPCBH2, a monoalkyl borane, can also be prepared in an enantiomerically pure form, often by purifying it as a stable complex with timida, tetramethylethylenidenamine. When this monoalkyl borane reacts with a procryl alkene, one of the two possible diastereomeric products, the new alkyl group plus the IPO group, is normally formed in excess due to the chiral influence of the APO group. This excess diastereomer can then often be obtained in high enantiomeric purity through crystallization or chromatography. Subsequent oxidation of this purified borane then provides the corresponding alcohol with the same high enantiomeric purity.
But you lose the expensive terpene part during oxidation.
That's the drawback. Oxidation also converts the original chiral terpene-derived group, the isopenocamphyl group, to isokinocamphyl. While this isn't a huge problem with inexpensive starting materials, the overall efficiency and atom economy of generating an enantiomerically pure product is significantly improved by procedures that can regenerate the original terpene, the chiral auxiliary, for reuse. This can be cleverly achieved by heating the intermediate dialkylborane, RBIPC, with acetaldehyde. This releases the ipene, which can be recovered and reused, and produces a diethoxyborane, RBOET2. The usual oxidation conditions then convert this boronate ester into the desired alcohol, ROH. It's a much greener approach.
Are chiral haloboranes useful too?
Yes, the corresponding chiral haloboranes derived from terpenes, like isopenocamphyl chloroborane and isopenocamphyl bromoborane, are also valuable for enantioselective hydroboration. Isopenocamphyl chloroborane can achieve respectable 45–80% C&ED play with representative alkenes. The corresponding bromoborane can achieve even better, 65–85% enantioselectivity with simple alkenes when used at very low temperature, 90 to 78 degrees C. Lower temperature often enhances selectivity.
Can you make chiral amines and halides this way too?
Absolutely. Procedures for synthesizing chiral amines and chiral halides have also been developed based on applying the amination and halogenation methods we discussed earlier to these enantiomerically enriched organoborane intermediates. For example, enantiomerically pure terpenes can be converted to trialkylboranes and then aminated with hydroxylamine sulfonic acid to yield chiral primary amines with good enantiopurity. And combining the power of catalytic and anti-selective hydroboration using catechylborane and a chiral catalyst with the amination process has provided certain amines with good enantioselectivity. In this procedure, the catechol group is cleverly replaced by a methyl group prior to the amination step, illustrating a strategic sequence of reactions to access chiral amines.
Okay, final topic for boranes. Hydroboration of alkynes. How do they react?
Alkynes are also highly reactive towards hydroboration reagents, often more so than alkenes. The most synthetically useful procedures for alkene hydroboration specifically involve the addition of a disubstituted borane, R2BH, like catechylborane, penacylborane, or dialkylboranes like 9-BBN or diacylborane to the alkyne. This is crucial because using borane itself, BH3, can lead to complications, such as multiple additions or the formation of polymeric structures, which are generally undesirable. Sticking to one addition is key.
Which reagents are particularly useful?
Catechylborane is highlighted as a particularly useful reagent for hydroboration of alkynes. One powerful transformation of the resulting vinyl borane adduct, boron attached to a double bond, is protonolysis cleavage by a proton source, typically just gentle treatment with acetic acid. This reaction specifically results in the stereoselective reduction of the alkyne to the corresponding cis-alkene. The boron is replaced by hydrogen with retention of configuration, and since hydroboration is syn, you get H and H added syn, which corresponds to the cis-alkane. This is a highly controlled and reliable way to make cis-double bonds.
What if he oxidized the vinyl borane instead?
Alternatively, an oxidative workup, typically with hydrogen peroxide and base, just like for alkyl of the vinyl borane adduct, gives ketones for internal alkenes, or aldehydes for terminal alkenes, RCHE, gives RCH2CHO. This proceeds via transient enol intermediates, which tautomerize. What's fascinating is that treatment of the vinyl borane with bromine, Br2, and base leads to the formation of vinyl bromides, alkenes with a bromine substituent. The reaction occurs with net anti-addition across the original alkene triple bond.
Anti-addition? Why anti here?
The stereoselectivity is elegantly explained by a mechanism involving anti-addition of bromine to the double bond of the vinyl borane first. This is followed by a second anti-elimination of bromide and the boron moiety, induced by the base. Two anti-steps result in overall net anti-addition of Bre and the H that replaced boron. It is important to note, however, that exceptions to the stereoselectivity have been noted in specific cases, so it's not always perfectly anti.
Can you make vinyl iodides?
Yes, the adducts derived from catechol are readily hydrolyzed by water to form vinyl boronic acids, RCHCHBOH2. These vinyl boronic acids are incredibly useful intermediates, especially for the preparation of terminal vinyl iodides. Since the initial hydroboration is a syn addition, and the subsequent iodinolysis, reaction with iodine I2, usually with base, occurs with retention of the alkene geometry. Iodine replaces boron where it was. The resulting vinyl iodides reliably possess the E configuration. The iodine and the remaining hydrogen from the original alkyne are on opposite sides of the double bond. The dimethyl sulfide complex of dibromoborane, BHBr2 and PNH3 and pinacolborane are also mentioned as useful reagents for synthesizing E-vinyl iodides directly from terminal alkynes via their vinyl borane intermediates.
What about hydroborating internal alkynes?
9-BBN can also be effectively used to hydroborate internal alkynes. The subsequent protonolysis with methanol provides a convenient and often highly selective method for the formation of a dis-substituted Z-alkene, cis-alkene. And just to reiterate, a large number of procedures that involve carbon-carbon bond formation have been developed based on these vinyl and alkyl organoboranes. These powerful C-C bond-forming reactions, like the Suzuki coupling, are discussed in detail in Chapter 9. This hydroboration chemistry is foundational for many subsequent steps.
Okay, let's move into the final section. Hydroillumination, carboillumination, hydrozirconation, and related reactions. These sound analogous to hydroboration.
Somewhat analogous, yes. Let's connect this to the bigger picture. Aluminum PN is the immediate congener, the element right below boron in the same group of the periodic table. Dialkylene and trialkyl aluminum compounds are commercially available and have significant industrial applications, especially in polymer chemistry. What's fascinating for synthesis is that they share some similarities in reactivity with organoboranes, which can be strategically exploited.
But there are differences.
Yes, there's a key distinction. Aluminum is considerably less electronegative than boron. As a result, aluminum reagents also exhibit characteristics similar to common organometallic reagents, like organomagnesium, Grignard, and organolithium compounds. This indicates a more polar metal-carbon bond with some anionic or negatively charged carbon character. Boron-carbon bonds are much more covalent. This gives aluminum reagents a sort of dual character, sometimes acting like boranes, sometimes like Grignards.
So hydroillumination, adding Al-H.
The addition reactions of alkenes with the dialkyluminium hydrides, R2ALH, providing an LH bond, occur much less easily than hydroboration. Only terminal or strained alkenes react readily at room temperature. With internal and branched alkenes, the addition often does not go to completion, making it less generally useful for alkenes compared to hydroboration.
What about alkenes?
In contrast, the addition of dialkylanes to alkynes occurs more readily. The resulting regiochemistry and stereochemistry are analogous to hydroboration, usually leading to syn addition with aluminum ending up on the terminal carbon for terminal alkenes. The resulting vinylanes alkenes with an aluminum group attached to one of the double bond carbons are synthetically useful. They react with electrophiles, like halogens, for example, I2, with retention of configuration at the double bond, allowing stereoselective synthesis of vinyl halides.
And carboillumination, adding an alkyl group in aluminum.
Right. With trialkyluminium compounds, R3Al providing an alkyl-al bond, The addition reaction across a double or triple bond is specifically called carboillumination, the net addition of an R group and AlR2 across the multiple bond. This reaction is important, but a key difference from hydroboration is that it generally requires a catalyst to proceed efficiently, especially for alkenes.
What do we know about the mechanism? Still a four-center transition state.
Computational studies of both hydroillumination and carboillumination have indicated a four-centered transition state for the addition, similar in geometry to borane additions. However, as we noted, aluminum reagents possess more nucleophilic character than boranes due to the lower electronegativity of Al. While the transition state for hydroboration is primarily electrophilic, boron-seeking electrons, the reaction with aluminum hydrides like CH3LH2 shows a closer resemblance to the reaction of a methyl anion attacking ethene, with the strongest interaction being with the alkene's LUMO, lowest unoccupied molecular orbital. This interpretation is consistent with observed relative reactivity trends, where the reactivity of alkenes towards hydroillumination decreases with increasing alkyl substitution, opposite to hydroboration, and alkenes are more reactive than alkenes toward these aluminum reagents.
Have good catalysts been found for alkene and carboillumination?
Yes, effective catalysts have recently been developed, marking a significant advance in making this reaction more practical. One such catalyst system involves zirconium complexes, specifically by pentamethylcyclopentadienyl zirconium dimethyl CP2ZrCH32, activated by tris, the fluorophenol boron, C6Fi3b. This system promotes the addition of trimethyl aluminum, Alme3, to terminal alkanes. The resulting alkyl aluminum can then be oxidized with O2 to yield an alcohol, effectively adding a methyl group and an OH group across the double bond.
Can this be done enantioselectively?
Yes. A chiral indene derivative of zirconium, specifically structure K shown in the text, has been most commonly used for asymmetric carboillumination. The chiral catalyst interacts with the trialkyl aluminum to generate a bimetallic species involving both Zr and Al, which is believed to be the true active catalyst. The detailed mechanism is still not fully known, but the Lewis acid character of zirconium is considered critical in activating the alkene. The reaction is further accelerated by the inclusion of partially hydrolyzed trialkyl aluminum reagents, known as alumoxanes like methylalumoxane, MAO, or isobutalumoxane, IBAO. These are oligomeric aluminum-oxygen compounds often used as co-catalysts in polymerization.
What can you do with the alkyl aluminum products?
The alkyl aluminum adducts formed from carboillumination are versatile intermediates. They can be protonalized, cleaved by acid, forming an alkane, or converted to halides with X2 or alcohols with O2. This methodology has been ingeniously used to create chiral centers in saturated hydrocarbon chains, which are frequently found in important natural products like vitamin E, vitamin K, and phytol. It allows for precise control of stereochemistry, specifically methyl branches, along a hydrocarbon chain. By converting the primary alcohol group, after initial carboillumination and oxidation, back to an alkene via oxidation and a Wittig reaction, the carboillumination sequence can be carried out in an iterative fashion repeatedly to introduce multiple methyl groups in a controlled stereoselective manner along a long carbon chain. It's a powerful chain-building strategy.
You mentioned alkene carboillumination is more widespread.
Yes, at this point in time, carboillumination of alkanes has found more widespread application in synthesis compared to alkenes, partly because it was developed earlier and perhaps is more reliable. The most frequently used catalyst for alkene carboillumination is bis-cyclopentadienyl zirconium dichloride, that's CP2ZrCl2, often called zirconocene dichloride. It is believed that a bimetallic species involving Zr-Al bonds is formed between the zirconium catalyst and the aluminum reagent. What's interesting is that even small amounts of water can significantly accelerate the carboillumination of alkenes. This acceleration may be attributed to the in situ formation of those activating alkenes. As indicated by the proposed mechanism, carboillumination of alkenes is a syn addition, meaning the alkyl group and the aluminum add to the same face of the triple bond.
And what about the vinylane products?
The resulting vinylanes are highly reactive intermediates. They react with various electrophiles with net retention of configuration. The original syn addition geometry is preserved in the final product double bond. Successful electrophiles include iodine, I2, to make vinyl iodides, epoxides, which get opened by the vinylane acting as a nucleophile, formaldehyde, and ethyl chloroformate to make unsaturated esters. Furthermore, as we will see in Chapter 8, these vinylanes can undergo powerful exchange reactions or transmetallation with other transition metals, like copper or palladium. This opens up valuable routes for the formation of new carbon bonds via cross-coupling reactions.
Can you give some examples from Scheme 4.1?
Sure. Entry 1 shows a reaction that was a critical step in the complex synthesis of the immunosuppressant drug FK506. The vinylylane intermediate formed by carbomethylation was subsequently transmetallated to a cuprate reagent for further CC bond formation, highlighting its versatility as a precursor. In entry 2, the vinylylane was cleverly used as a nucleophile to open an epoxide ring, effectively extending the carbon chain by 2 atoms with control over stereochemistry. Entries 3 to 5 demonstrate how the vinylylane adducts can be efficiently converted to vinyl iodides using iodine, providing a stereoselective route to this important functional group. And entry 6 shows the vinylylane being converted to an 8 reagent, making the aluminum negatively charged by adding another alkyl group prior to reacting with formaldehyde. This showcases a strategic sequence of transformations needed to achieve specific reactivity with certain electrophiles.
Okay, lastly, hydrozirconation, adding Z or H.
Right. Derivatives of zirconium that contain a zirconium hydrogen, ZRH bond, also possess the ability to add across alkenes and alkenes. This reaction is known as hydrozirconation. The reagent most frequently used in synthesis for hydrozirconation is bis-cyclopentadienido hydrozirconium IV chloride, often abbreviated as CP2ZrHCl, and commonly known as Schwarz's reagent. It's a stable, weighable solid. The active hydrozirconating species can also be generated in situ by the reduction of CP2ZrCl2, zirconosine dichloride, using various reductants like lithium aluminum hydride, LiAlH4, or lithium trialphyl borohydride, like 3BH, sometimes called superhydride.
How does it react with alkenes?
Alkenes readily undergo hydrozirconation with Schwarz's reagent. With internal alkanes, this reagent initially gives a regioisomeric mixture, meaning it can add with Z on either side of the original triple bond. However, a very beneficial phenomenon occurs. Isomerization happens relatively rapidly under the reaction conditions to give predominantly the less sterically hindered isomer, where the bulky zirconium group migrates to the less crowded position on the resulting double bond. This provides a way to achieve good regio control even if the initial addition isn't selective. The resulting vinyl zirconium adducts are highly reactive and can be transformed by reaction with various electrophiles, such as N-chlorosiliconamide, NCS, and bromosiliconamide, MBS, and iodine, I2, to yield the corresponding vinyl halides with retention of configuration.
And alkenes.
Alkenes are generally less reactive towards hydrozirconation compared to alkenes. Reactivity also decreases as the degree of substitution on the alkene increases, similar to hydroillumination. What's very useful for alkenes, though, is that the alkene zirconium adducts formed from internal alkenes will also undergo an isomerization process, similar to boron migration. They eventually lead to the terminal derivatives, where the zirconium migrates to the very end, the primary position of the carbon chain, the thermodynamically favored, less sterically hindered position. This is synthetically powerful for functionalizing the end of a chain.
And these zirconium reagents are also used for CC bond formation?
Yes, alkynyl zirconium reagents are incredibly valuable for carbon-carbon bond formation reactions, but these usually involve transmetallation reactions. The zirconium is exchanged for another metal, like copper or palladium, which then facilitates the actual CC bond formation step via processes like cross-coupling. These fascinating transformations are discussed in detail in Chapter 8. Hydrozirconation is often just the first step in a longer sequence.
Wow. We've just completed an extensive and pretty deeply structured deep dive into the fascinating world of electrophilic additions to carbon-carbon multiple bonds. We began by unpacking the fundamental principles, didn't we? From Markovnikov's rule and its elegant carboxylic basis, to the delicate dance of stereochemistry in those bridged halonium ions. We explored how those subtle forces of stability in 3D interactions can completely dictate a reaction's outcome.
We certainly did. We then moved through the powerful synthetic applications of oxymercuration, which provided that milder, more selective alternative to traditional hydration, avoiding those nasty rearrangements. We uncovered the surprising behavior of amines, where orbital alignment dictates reactivity in a non-intuitive way. And we spent significant time on the anti-Markovnikov regioselectivity of hydroboration, which allows chemists to place functional groups in precisely the opposite positions compared to traditional additions, giving unparalleled control.
And we concluded by exploring the frontiers, really, of hydroillumination, carboillumination, and hydrozirconation. We witnessed how these metal-mediated additions provide, again, unparalleled control over molecular architecture, including that exquisite challenge of creating chiral centers, those crucial 3D arrangements so vital for pharmaceuticals and advanced materials.
And what's truly clear, I think, is that these reactions aren't just abstract concepts confined to textbooks or exam questions. They are the foundational tools. They're strategic building blocks that allow organic chemists to construct incredibly complex molecules, everything from life-saving pharmaceutical drugs that require specific enantiomer, to advanced materials with tailored properties, and even intricate natural products isolated from nature. These are the reactions that enable innovation in chemistry, allowing us to, well, build the molecular world around us with truly astonishing precision.
So, what does this all mean for you, the listener? The next time you encounter a new organic molecule, perhaps mention in a news report about a breakthrough drug, a novel material, or maybe an environmental solution, I want you to consider the unseen journey it underwent. Think about the intricate, multi-step synthetic pathway that brought it into being. Imagine the strategic atom-by-atom decisions, the precise placement of every functional group, the control over three-dimensional shape, all achieved through the very reactions, the fundamental principles we've unpacked today. It's a profound reminder, isn't it, that even the most complex structures are built, one incredibly precise addition at a time. This depth of understanding, this control, that's the true artistry of organic chemistry.
Beautifully put. Thank you for joining us on this extensive deep dive into the world of electrophilic additions. We hope you found this exploration not only incredibly informative, but maybe also deeply inspiring. We believe that understanding these fundamental principles is key to appreciating the elegance and the sheer power of molecular construction.
Until our next journey into the world of chemistry, keep learning, keep questioning, and keep diving deep